Hi guys, welcome to the post-contest discussion of the Codeforces Round 969. This is TLE Eliminators and I am Abhinav Kumar. So let's get started with the first problem. So today we'll be discussing all the 6 problems of Div 2 for this contest. So let's discuss the first problem. Dora has a set as containing integers. So like in this problem, what it's given that you are given a range L and R. So as an input, you are just given 2 integers L and R. And what does that means? That means all the integers in the range from L to R. So if it is 1, 3, all the integers in the range 1, 3, that is 1, 2, 3. All of those are in a set S. So set S represents all the integers in the range from L to R. And then what then C allows you to perform the following operations. Then you can perform this operation, that is select 3 distinct integers A, B, C from the set S such that this condition is satisfied. What does this means? This just means that for all the 3 integers, if you take any 2 integers, they are co-prime with each other. Just GCD of AB is 1, GCD of BC is 1. It means A and B are co-prime, B and C are co-prime, A and C are co. So all the 3 integers are co-prime with each other. That is the condition. If the 3 integers satisfies that condition, you can pick these 3 integers and remove them from the set. That would be one operation. Remove these 3 integers from the set. So this is one operation. What is the maximum number of operations you can perform, that is asked in the question. Okay, so like let's say you have you are given as an input, you are given L and R. So let's say L is 3, R is 8. It means in the set S, it contains 3, 4, 5, 6, 7, 8. This is your set S. All the integers in the range from L to R are contained in the set. Now, you have this set. What you need to do, you need to perform operations. So to perform the operations, you would pick 3 integers A, B, and C such that A and B are co-prime with each other. Just that is GCD of A and B is 1. So like if you take 3 and 5, their GCD would be 1. So you can have 3 and 5 and you have to take 3 integers. GCD of AB should be 1, GCD of BC should also be 1, and GCD of AC should also be 1. So the 3 integers should be co-prime to each other. So for every pair, they should be co-prime. So maybe you can pick 3, 5. Uh, let's say here you pick 3, 5, and 7, let's suppose. So 3, 5, and 7. You pick any 2 integers, their GCD would be 1. You pick any 2 integers, their GCD would be 1. So you can pick these 3 integers and perform your operation. So once, let's suppose you pick 3, 5, and 7 and perform the operations, these 3 would be removed from the set. You would be left with 4, 6, and 8. Now, let's say you perform this operation and you are left with 4, 6, and 8 after this first operation. Now, again, to again perform an operation, you would have to pick 3 integers and perform the operation. Now, here you have only these 3 integers. Can you pick these 3 integers? Can you pick 4, 6, 8? No, you cannot pick because GCD of 4 and 6 would be 2. They are not co-prime with each other. So you cannot pick them. GCD of 6, 8 would also not be 1. So you cannot pick like this. So here, if you perform 3, 5, 7, you can perform only one operation here. But what you need to do, you need to perform the operations in such a way so that you can perform maximum number of operations. Basically, you need to find the maximum number of operations you can perform in the set. So you need to select those 3 integers so that you can form basically groups of 3 integers, maximum number of groups of 3 integers, so that the 3 integers satisfy this condition. You need to find maximum, you need to divide the set into maximum groups of 3 integers like this. That's what you need to do basically. So like let's see, to satisfy this condition, like to solve this problem, you need to just crack one simple thing, that when would 3 integers satisfy this condition? Okay, so you are given a range from L to R. That is, you are given always given some consecutive integers. It's never like you are given some set of 4, 5, 8 like this. You are always given a set of consecutive integers. Initially, your set is always consecutive integers from 3 to 8. So if you have consecutive integers, let's say you have this 3, 4, 5, 6, 7, 8. So what would be the best to pick? Like, let's say you have a 9 also. In this case, the best thing would be if you pick 3, 4, 5, that would be GCD of any two would be 1. Then you can pick 7, 8, 9. Here, you can perform two operations by picking 3, 4, 5, and 7, 8, 9, and then 6 would be left. So you can perform two operations like this. How did I decided that? So that is you need to find what all three integers you can pick. So first thing is, if you in your ABC, if two of the integers are even, let's suppose there are two integers which are even, then definitely for any two even integers, their GCD would be 2. They won't be co-prime. So the first thing, like you can notice, obviously, that you cannot have two even integers. You cannot have. You can at max have one even integer. If you have two even integers, their GCD would not be 1. They would not satisfy the condition. So in the set of these three integers, at max, there can be one even integer, not more than that. So either you have three odd integers or two odd integers and one even. These are the only two possibilities. Now, let's say you take two odd and one even integer. Now, another thing it should satisfy is if you take two odd integers like 3 and 9, their GCD would be 3. So you should not take it like this. So the two odd integers that you take, they should not have a GCD of they should have a GCD of 1 basically. So one thing you can notice, since you are given consecutive integers, if you take any two consecutive odd integers, let's say you take 3 and 5, their GCD would always be 1. Let's say you take 5 and 7, their GCD would be 1. If you take 7 and 9, their GCD would be 1. Like from 1 and 3, if you just keep on looking at this, if you take any two consecutive odd integers, they would always be co-prime. This is a property like you can notice, or like it is intuitive. If you don't need a proof for that, like if you take any x and x plus 2 where x is odd, uh, for them to have some common factor, like if they have some common factor, first of all, they are out, they wouldn't have 2 as a common factor. So at max, they would have 3 or more than 3 as a common factor. And if you add 2 to them, if 3 is a common factor of x, then plus 2 would never be a multiple of 3. If x is a multiple of 5, then plus 2 would not be a multiple of 5. So they would never have a common factor. So if you take two consecutive odd integers, they would always be co-prime. Now, what you can do, you can take an odd integer x and its next odd integer would be x plus 2. Now, for every, you need to have three integers a, b, c. For the third integers, now you took two integers x and x plus 2. For the third integer, you can have an even integer. The third can be an even, can be an odd. Now you need to maximize your operations. So between x and x plus 2, there is x plus 1, which is an even integer. I'm assuming that x is odd here. So whenever you take x and x plus 2, two consecutive odd integers, there would be an even integer in between. So you should utilize that number instead of taking another odd integer that can be utilized in some other operation. So basically, you just need to choose like this. Take an odd integer, 3, and the next two integers. So x, x plus 1, and x plus 2. Always take these three consecutive numbers such that there are two odd and one even integer. If you take like this, you can just have maximum number of operations. You can perform maximum number of operations. Okay. So basically, if you had this from what I did here, you can see here I had from 3 to 9. I took this, since this 3 was odd, I took 3, 4, 5. Then I cannot start with 6, because if I start with 6, I would have two even integers. So I left this 6 and then I started with 7 again, then 7, 8, 9. So basically, in the range, what is the maximum number of operations you can perform? That is number of pairs of odd integers that you get. So if you have a count of odd integers in the range from L to R, if C odd represents the count of, you can obviously find the count of odd integers in the range from L to R. If you can find this, then your answer is just going to be this count by 2, because every time you would use two odd integers and a even integer in between them. So every operation you would utilize two odd integers. So C odd by 2, the seal of this would be your final answer. So, and what would be the count of odd integer? So you can obviously have two cases. For the range of L to R, the number of the size of this range is R minus L plus 1. This is the size of the range. Now, uh, if this range is 3 and 9, now the size of the range is 9 minus 3 plus 1, which is 7. Okay, so this 3, 4, 5, 6, 7, 8, 9. Here there are 7 numbers, 1, 2, 3, 4, 5, 6, 7. Okay, the size of the range is 7. How many odd integers are there? It would be either 7 by 2 is 3.5. So it would be either 3 odd and 4 even, or 4 odd and 3 even. So if it is starting from odd, it would be seal. So here you would have 4 odd integers. And if it is starting from even, if it was 4 and 10, if it is starting from even, then there would be 3 odd integers. So just check if L is odd, then you would say number of your C odd, the count of odd integers would be the size of the range by 2, the seal of this. And if L is even, then your C odd is going to be the size of the range by 2, the floor of this. Okay, once you've computed your C odd, your final answer is C odd by 2. So here also I'm doing by 2. So like you can just directly write your final answer as R minus L plus 1 by 4. You can just directly write. You are doing by 2 again. So either the seal of this or the floor of this, like depending on where L is odd. So like you can just see my code. What I did, if L was odd, I just did L minus minus, so that I include, uh, I start from one less. So I don't have to do the if else condition. I just directly take R minus L plus 1 by 4 as my final answer. So, or what you could have done, you could have written if else. If L is odd, you could write plus 2 here in case when L is odd, so that you if you want to take the seal of uh, this division would always give you the floor. If you want to take a seal, you just do a plus 1 and then divide. That would give you the uh, floor basically. So what I did, I just decreased L by 1 in case of odd. So it would like this R minus L would, this range would obviously increase by 1. It is equivalent to taking R minus L plus 2. Okay, so that's what I am doing. Just you had to take care of this odd and even case. When L is odd, you would have one extra integer in your range, that odd integer. That's why I did L minus minus. And my answer is the size of the range by 4. Okay, I hope it is clear. If there is any doubt, you can ask. Uh, like Prakhar, we can discuss those things maybe after the session. If you have doubts in this problems, you can ask. After the session, you can ask other doubts. Okay, I hope the problem A is clear to everyone, so we can move to the problem B. Okay, in problem B, we are given like we are given an array. So after receiving yet another array as a birthday party index. Okay, in this array, what you can do, you can perform. There are total m operations that you have to perform in the array, and the operations are of two types: plus L. So plus L are what the range. Okay, so all the that are in the range from L. Okay, so this means all the values that are from L to R, those values by plus LR means all the, it is AI. So all the values that are in from L to R decrease values by 1. So have this as a total array, and your operation is plus 2, 4. So all the values that are range from 2 to 4, increment them. 7 is not in the range from 4, 1 is not, is in the to 4, increment 4 was in the range 4, incremented that to 5. In the range from 2 to 4, incremented that. So that's how it is minus, then you decrement it from 1 to 10. All the integers were in the range from 1 to 10. So all of them incremented by 1. So that's the to perform. Now, curious about the maximum value in the array, please help us find. So we are given here is we are given an initial and then m that we perform. Every you need to operation maximum current array. After the operation, what's maximum value in that answer? Let's this first look what. Sorry, I had got disconnected. Am I audible? No. Yes. Okay, so sorry, I had got disconnected. I'll discuss the problem B again from the start. I'm audible and my screen is visible. Just write yes, yes for both. Okay. Okay, so problem B, what we are given that we are given an array, and what we need to do in the array, you can perform two types of operations. So an initial array is given to you, then two types of operation. One type is plus LR and minus LR. So if the operation is plus LR, then for all the values that are in the range from L to R, you would increment that. And for minus LR, all the values that are in the range from L to R, you would decrement that. So for example, if you have this as your initial array and your operation is plus 2, 4, what you would do, all the values that are in the range from 2 to 4, that would be incremented. So 7 is not in the range from 2 to 4, 1 is not. Now 3 is in the range from 2 to 4, that would be incremented to 4. 4 was in the range from 2 to 4, that would be incremented to 5. Same way 3 incremented to 4. So this is the array obtained after performing plus 2, 4. Similarly, if you perform operation of minus 110, all the values in the range from 1 to 10 would be decremented by 1. So all of them were in the range from 1 to 10. All of them got decremented by 1. This is the operation that you need to perform on the array. Now index is curious about the maximum value in the array. Please help her find it after each of the m operations. So you are given your initial array and there are m operations given. After each operation, you need to find after the first operation for your current array, what's the maximum value? After the next operation, your current array is changed. Now for the current array, what's the maximum value? That you have to return basically. So if you take a look at this was your first test case. So this is the array given to you and these are the m operations. Okay, so initially your array is 1, 2, 3, 2, 1. So the first operation says plus 1, 3. So all the values in the range from 1 to 3 would be incremented by 1. So 1 is in the range, it would be incremented, 2 would be incremented, 3 would be incremented. So all of them were in the range from 1 to 3, they all got incremented. So this is your array obtained after the first operation. Now what is the maximum value in the array? It is 4. So answer after your first operation, you would answer 4. Now, your second operation says minus 2, 3. So all the values in the range from 2 to 3 would be decremented by 1. So this got decremented, this got decremented. Now 4 is not in the range, it won't be decremented. It would remain 4. 3 got decremented and 2 got decremented. So this is your array after the second operation and the maximum value is 4 here. So you would answer 4. Same way, plus 1, 2. So these all would be incremented. This would remain same, incremented. Again, your maximum value is 4. You would answer 4 plus 2, 4. It would be 3, 4, 5, 4, 3. All of them got incremented by 1. And now your maximum value is 5. You would answer 5 minus 6, 8. So in the range from 6 to 8, there are no values. So the array would remain the same. Your answer would be 5. So for this particular test case, you would answer this 4, 4, 4, 5, 5. You can see it is 4, 4, 4, 5, 5. So I hope the problem is clear what you need to do. Okay. Now, first you would think you can just do the brute force that have your initial array and after every operation, just check for every I. If they are in the range, just increment by 1 and then take the maximum. But what would the time complexity of that be? For every query, there are m number of queries, and in every query, you would have to check every element. So check every element and increment it, then take the max. So that would be O of n. So your overall time complexity would be n into m if you do the brute force approach. And you can see the constraints of the problem that n is 1e5, m is also 1e5. So obviously O of m into n would not be accepted here. You need to optimize the approach. Now, what you can do to optimize? So you just need to notice a small thing here that since there are m operations and m is up to 1e5, so for every operation you need to do something in O of 1 type or one O of 1 or O of log n. You cannot go O of n. So you cannot go to and perform the operations every time. So how can you optimize this? So one thing you need to notice here is whenever you perform an operation, the final answer that you need is only the maximum value after the operation is performed. Okay, you don't care about the other values. Okay, so here the maximum value was 4. You care about 4. Then 4, 4, 5, and 5 was the next maximum value. So you only care about the maximum value. Now, when would your maximum value change? That only you need to determine. For your initial array, your maximum values was 3. When can this maximum value change? Is when you perform some operation on this 3. Either you would decrement this 3. Okay. So either you would decrement this 3 to 1. If you perform some minus operation such that this 3 is in the range. Now, it would be decremented to 2. Now, can it happen that if your maximum value is 3 and there is some operation of, let's suppose, minus LR type such that this 3 is in the range of L to R, then after this operation, you can definitely say that your new maximum value would be 3 decremented by 1, that is 2. Can it happen that there is some element which is greater than 2 in the array? You already know that 3 was your maximum value. So there was no value greater than 3 in the array. Now, once you decremented all values in the range from L to R and 3 is in the range. So maybe you may have multiple 3s here. Maybe you have another few 3s. All of those 3s would be decremented to 2. That's for sure because the operation is performed on the whole array. And if there is any 3, if 3 is in the range from L to R, all of the 3s would be decremented to 2. And there is no value greater than 3 in the array. So you can say my new maximum value is 2 now. If my previous maximum was X and I perform an operation of minus LR such that X is in the range from L to R, then I can say my new maximum value would be X minus 1. Now, when you perform the operation of plus LR, then what would happen? If let's say my previous maximum value was X and I perform a plus LR. So let's say X was 3. So 3 was my previous maximum value. I perform a plus LR says that 3 is in the range. Now I know before my maximum value was 3. Now I am performing a plus operation. It means I'm incrementing the values by 1. So if this 3 gets incremented by 1 and gets incremented to 4, 4 would be my new maximum value. If there is some 2 that is getting incremented to 3, any value would get incremented by 1. So no value can reach 4 or greater than 4 if it is less than 3. Only all the values which were 3, they would reach 4. So your maximum would never get incremented by more than 1. So if your maximum value is in the range, then if it is a plus operation, increment the maximum value. If it is a minus operation, decrement the maximum value. Because on every operation, you are only incremented by +1 or -1. So it would not happen that there is some value 2 which is less than 3, and after some plus operations, it goes above 3. Either both of them would get incremented, or only this 3 would get incremented, or this 2 would get incremented to 3. It can get equal to 3, but it would never cross 3, because for it to cross 3, it should happen that there is no plus operation on 3 and there is some plus operation on 2, but it's happening one by one. So it would cross through 3 only. It would become equal to 3. Once it's equal to 3, it would go along with 3. So what I'm telling is, whatever is your maximum value, you just perform the operation on that value. You don't need to care about other values. If your maximum value is 3, just ignore all the other values, perform your operation, assuming 3 is the only value in your array. Then you would get whatever answer you're getting, that would be your final answer. Why? Because it would never happen that some value crosses. If let's suppose your operation is +1 2, okay, and there is 3 as the maximum value. So 3 is not in the range. So in the range, I discussed for both of them that why it would always be your answer. If it is not in the range, that also I'll discuss. If 3 was not in the range from 1, in the range of L to R, then what would happen? At max, the range is 1 to 2, and this 2 would get incremented to 3. It would never cross 3. So 3 would remain your maximum value. And if there was some minus operation on some different range, it would get decremented. Your 3 would remain your maximum value. So your what you can say is, you only need to consider the initial, in your initial array, what the maximum value is. Just consider that as your single value, perform the operations on that value, and whatever you are getting, that would be your answer. Uh, okay. So I hope it is clear why we are only considering the maximum value. So you can now, if you are considering only one value, it would be O of M into 1. Just it's constant operation for every uh, query. So in O of M, you can perform this. So you can look at the code now. So N and M input, these are all the input. And then I just, in MX, I just took the maximum element for the whole array A. This all A just means X dot begin, X dot end. So it's A dot begin, A dot end. I'm just taking the maximum element from the array A in MX, and I would perform operations only on this MX. So uh, inside my while M minus minus, so in every query, I would take CLR. If C is plus and MX is in the range from L to R, then I would do MX plus plus. If C is minus and MX in the range of L to R, then I would do MX minus minus and just see out MX for every operation, for every query. Okay, so I hope this problem and this code is clear. Okay, so if in the question, if operation did +-2 or more for LR, then what could we have done? So maybe that would be a different question if you are allowed to do +2, -2 and all. Then you cannot handle like this. But here in the problem, it was given like this, only to think that it would never cross. If it is +2, +3 and all, then maybe it could cross. You would have to do the brute force thing. Okay. So I hope this problem is clear. We can move to the next problem now. So in problem C, what we have is that Dora has just learned programming language C++ and she understands it. Okay, so what we are basically given is we are given an array and two constants A and B. So A and B are two constants and there is an array C. So what you can do that here again you can perform operations. In every operation, what you can do, you can just select an integer I and increase Ci by A or increase Ci by B. So you can increase, you can select any element of the array and increase that element by A or by B. These are the two operations that you can perform. So either increase it by A or increase it by B. That you can do in a single operation. Now A and B are the constants that are you are given before only. Let's define range of array D as max of Di minus min of Di. So it's the obvious thing that the range for an array is the maximum element minus the minimum element is called the range. So here maximum element was 4, minimum element was 1. So 4 minus 1, 3 is the range of this array. For this array, 8 minus 1, 7 was the range for this array. Okay, so the definition for range is given. Now, what you need to do is after any number of operations. So the number of operations you can perform is up to you. You can perform any number of operations. You can even perform zero operation or infinite number of operations. Dora calculates the range of the new array. You need to help Dora minimize this value. But since, okay, so basically what you need to do is just perform any number of operations and find the minimum range you can get. So it's up to you what operations you need to perform. You need to pick, you can pick either A, either B. Just do any type of operations and finally come up to an array which has the minimum range. So just minimize the range of the array by performing the operations. That's what the problem states. Okay, so let's take this second test case and see. Okay, so this is NAB. So you are given this array C and two constants A equal to 2, B equal to 3. So what you can do, you have this array 1, 4, 1, 3, 4, 6. Now, currently, what's the range of this array? Currently, the range of this array is 6 minus 1, which is 5. Okay. Now, you need to decrease this range. How can you decrease this range? To decrease this range, you have operations of two types. Either select an element and increment it by A, so increment it by 2, or select an element and increment it by B, incremented by 3. Okay, you have these two types of operation. You can perform any of them and basically find what's the maximum minimum range you can get. So here what you can do, you can maybe increase this one by let's say you take B and increase it to 4, and then you take A, increase it to 6. This 3 also can be incremented by 3 to 6. This 4 can be incremented by 2 to 6. So this way you can have this 6, 6, 6. So if you have all equal, your range would be 6 minus 6, which would be 0. So 0 is the minimum range you can obtain. So for this test case, you can actually get all the elements to be equal to 6 in some by through some way of operation. And then you can make the range 0. So 0 is the minimum range you can get for this test case. Here your answer was 0. Now, maybe in some case you cannot get a 0. You would never, it would not be that in every case you would get a 0. So what you can do here, I hope the problem statement is clear what you need to do. Okay. Uh, so now what you can do, let's say instead of these two values, A and B, you have just a single value. Like for the first test case, you were given just uh, both A and B were equal to 5. So let's say, let's solve the problem for this type, and then we would see what we can do if you have different A and B. So if you have A and B both are same, it means you can, if you select A or B, they both are same. So there is only one type of operation, that is do a plus 5 to any element of the array. That is the only operation you can perform in this case if your A is equal to B. So let's solve the problem for this simplified version. Then we would see how can we solve for the when A and B are different. So if you have been given the simplified version, 1, 3, 4, 4, and you have A and B both are equal to 5. So what you can do in every operation, you can do a plus 5 only. You can make it 6, you can make it 8. Okay, leave it 4, 4. You cannot do any other operation. So by doing plus 5, you need to determine the minimum range. Now, what is a range? So if you just look at it, so on a number line, if I draw 1, here 3 and 4. Okay, so the range is the maximum value minus the minimum value. This length is my range here in this case. Now, how can I reduce this range? Here my range was 3. So if I do a plus 5 here, make it 6, I can make it jump to 6 somewhere here, and that would be cancelled. So if I make it 6, it would jump to 6. 6 would be somewhere here, and this would be cancelled. So now my range would be this 6 minus 3. It would remain 3. So let's say I had one more value here. Instead of this 4, let's say I had 10 here. Okay. So now, okay, I had 1, 3, 4, and 10 here. So now what I can do, initially my range is 10 minus 1, which is 9. So by performing the operations, I can bring the values closer. If I bring them closer, then I can reduce the range. So I can make this 1 jump to 6. 6 is somewhere here. I can make this 3 jump to 8, 4 jump to 9. So I can now cut these values and made them jump to here. Now the range has become 10 minus 6, which is 4. We have reduced the range. So basically, to reduce the range, we need to bring the values closer to each other. Now, how can we bring the values close? Now, the only operation we can perform is a plus 5. So one thing you can notice is always we can bring the value. If I can perform an operation of plus 5, we can always bring the values as close as a range of 5. My answer would never exceed 5, that I can guarantee, because by doing plus 5, we can just divide this number line into range of 5s. I can just divide into 0, 5, 10, 15, 20. So I can just divide it into groups of 5. So I can bring all the values into a single group of 5. That is for sure. So if I have some values here, 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 by every jump, if it is somewhere here, it would jump to exactly the same location in this group. So if it is plus 1 from this left range, if it is 1, after the jump, it would be 5 plus 1, 6. After the next jump, it would be 10 plus 1, 11. So one thing is for sure, that whatever the maximum value is there, to whichever group that belongs, we can bring all the values into that group. Here my maximum value was 10. It belonged to this group. So we brought all the values from this group to this group. So I can always reduce my range to less than equal to 5. That's the first thing. Now, how can I reduce it further? So if once I have brought into a single group, now what would be the values inside that group? That is, you can just like, from this intuition, you can just see that inside the group, it doesn't matter what this value is. Your range would be the minimum and difference between minimum and maximum. You can just make all the values plus 5 and jump to this group. You can just jump to next groups by doing a plus 5 to all the values. So basically, this does not matter for your range, only the difference matter. So if I have this value 6, 8, 9, 10, once I made them 6, 8, 9, and 10, now I can just write them as, if you do mod 5, you would have 1, 3, 4, and this 10 can be written as a 0 or 5 also. Okay. So if I made them jump to this side, it would fall in this group. So its mod would be 0. So if I made them 11, a plus 5, 13, and 14. So this 10, 11, 13, 14 would be, this 10 mod 5 would be 0. 11 mod 5 would be 1, 13 mod 5 would be 3, 14 mod 5 would be 4. So one thing you can clearly notice is, if you take modulo A, whatever value you get, that is the value that you need to consider. So basically, you can write every integer as some multiple of some n times A plus some value, which is m. I'm telling that ai mod or ci mod a is m. If m is the remainder, or let's say r, if r is the remainder, then I'll say I can write every number in this form, n times a plus r. So this n times a would get cancelled from every number, and this r would be the only thing that matters. So basically, to transform this, what I can do in this array, I can just take modulo a, and whatever remainder that I get, I can just use those remainders as my numbers, and then just find what's the minimum range I can have from those. So there again, you would have two options. So like I'll show you. If you had this 6, 8, 9, 10. Okay. So this 6, 8, 9, 10, if this was your initial array, let's suppose, then and your A was 5. You took mod 5, it became 1, 3, 4. Okay, and this 10 became 0. Okay. So either what you can do, you can have this 0, 1, 3, 4, or you can make this 0 jump to 5. Okay, so one option is this range, the range from 4 to 0, or make this 0 jump to 5, then it would be this range, or make this 1 also jump to 6. Okay, then it would be this range, or make this 3 jump to 8, then it would be this range. So once you have taken mod 5, then either it would be from this 0 to, either it would be from 0 to 4, or 1 to 5, or 1 to 6, or 4 to or 1 to 3 to 3 to 6, or 4 to 8 likewise. Okay, what you can do is just take mod 5. You got 0, 1, 3, 4. So and just take the maximum among these. Either 4 minus 0 is your answer, or increment is 0, make it 5. So now 5 minus 1 is your answer, or make it 6. 6 minus 3 is your answer, or make it 8. 8 minus 4 is your answer. Or okay, these are the only cases. So what you can do is, among them, whatever the minimum value is 3, so 3 would be your final answer for this test case. Okay, I hope this logic is clear. So why we did this mod A is because you would always jump in the range from plus A plus A. You would always jump in multiples of A. So if initially your remainder is R, after every jump, your remainder would remain R only. Your remainder, your mod A would never change. It would always be in this form, NA plus R. Or if you add a, your this N would increase. So if you make the value of N same for all of them, they all would fall in a single range like this. And once they fall in a single range, then you can just decide whether to have this as your answer, or make the first one jump there and this as your answer, second one jump there and this. So among them, you can take the minimum and then say what your final answer is. Okay, so this was the case when we had a equal to b, then we can do this. Now, but when we have a equal to b, we can just take mod a for every value, and then whatever the values that we get, sort them, and like this, take the minimum. Now, what if in your original question, you were given A and B, there are two separate operations. Either you can do a plus A, or you can do a plus B. That is, you can see, you can move, if you have some value, X, you can move in the range of X plus A, X plus 2A like this, or maybe you can remove plus B. So either you can move plus A, or you can move plus B also, X plus 2A plus B. You can move in any range. So if you have X initially, finally you would have X plus maybe N times A plus N1 times A plus N2 times B. This would be your, like in general, you can say if you have performed the A operation N1 times and B operation N2 times, so your value would be something like this. So what you can say is your any value would be something like this. Now, when you had only A or only B, you said that if you had only A, it was X plus N times A. And you just said that modulo A would always be X here. It is constant. Your modulo A was constant here. Now, but when you have something like this, here you cannot say your modulo A is constant because through B you can change that. And you cannot say your modulo B is constant because through A you can change that. But what is the thing that remains constant that you need to identify here? So if you have something like this, like if you solve a few more problems, you would get this property and this intuition why I'm saying this is that your the constant that would remain here is that x plus n1 times a plus n2 times b mod of what? If you take the GCD of a and b, this thing, the modulo this would remain constant. Why? Because if you take the GCD of A and B, you can write A in the form of some multiple of, if I'm telling that GCD of A and B is G, I can write A as some, let's say some multiple of G, and I can write B as some other multiple of G that I can write. So this is simplified to N1 M1 times A plus N2 M2 times G times G. So instead, so A is some multiple of the GCD, B is some multiple of the GCD, and GCD is the greatest number for which we can write A and B as some multiples. Okay, that's what GCD is. That's why I'm taking it GCD. So if you look at this number, you take modulo G, this would remain constant. So you can basically say that if you have A and B as the operations that you can perform, and G is the GCD of A and B, then you can say that you can bring all the numbers in a range of G. So your final answer is going to be less than equal to G. So in the first case where we had A and B equal, now when you have A and B not equal, then what you can see, you can say you can take G as the GCD of A and B and apply the same algorithm that you did, taking G as your A equal to B equal to G, let's say, taking G as your value that you can do. Because if you, let's suppose your A is 5 and B is 10, your GCD would be 2. So it means you can bring all the values in groups of 2. So you can divide the number line in twos. So whatever values are, you can bring all of them in a single group of 2. How? You can, through 5 and 10, you can always make groups of 2. If you if you have some, let's say some CI, some value is 7, and 7 mod 2 was 1. So you need to bring the, so you can assume that doing a plus A and plus B is equivalent to doing plus 2 all the times. Why? Because sorry, GCD was 5 here. I'm sorry, I'm sorry. GCD of 5 and 10 was 5, not 2. Okay. Instead of taking 5, let's say it is 10 and 15. Let's say it is 15 and 10. Okay. GCD of 15 and 10 is 5. So what you can do is you can use, you can always do a plus 5. How you can do that is the difference between them is you can take either sum or difference and likewise just operate them. So if you have 7, 9, and let's say the same numbers that you had there, what they were 6, 8, 9, 10. Let's say you had these numbers. Okay. Now, instead of giving A equal to B equal to 5, I gave you A equal to 10 and A equal to 15 and B equal to 10. Okay. Now, what I'm saying, giving this is equivalent to giving A equal to B equal to 5. Why? Because what you can do is you can bring them in a range of 5. How? You have this 6. Okay, let's say you can always increment them. So modulo 5 is 1. You have to bring them in the range of 1, 3, 4, and 0. This is what you need to do is, so this is already 0. So here they were already in a single group. Okay, let's say it was 1 year. Okay, and 3 year. Okay, they were in different groups now. So you can do a plus 10, make it 11. Here you can do a plus 5, make it 8. So maybe leave it like this and like this. Sorry, not you cannot do plus 5, you can do only plus 15. So it became 18 here. So whenever you need to do a plus 5, so what you can do, you can do a plus 15 and increment all the other values by plus 10. That would be same as doing a plus 5, because in your range, your absolute values does not matter. The difference matters. So you can just increment all the values by plus 10, and the value that you needed to increment by plus 10 can be done plus 15. All other values can be done plus 10. This way you can increment a value by plus 5. So basically through A and B, if you take their GCD, that is the number you can manipulate basically. I hope how it's clear. Like maybe through some other example, I can show you. If A was 6, B was 9, their GCD is, okay, let's say it's 15. Their GCD was 6 and 15. The GCD was 3. So you can always do a plus 3. I can say you can always do a plus 3. How? You can do 3 times plus A. Let's say 3 times plus A would make plus 18. All the other values you can do a plus B, plus 15. So if you want to make some value I, you want to make a plus 3 to some value I, just do 3 times A, and all the other values do 1 time B. That way 18 minus 15 is 3. So that you can do. So you can actually perform a minus operation here. It's not actually minus, but make doing a plus B to all other values is equivalent to doing a minus B to that particular I value. Okay, I hope it is clear. So like, I hope it is clear. If you have any doubts, you can ask. Uh,
So,
yeah,
so after we get it in a range of 0 to G,
yes.
we have to check for each element, like we have to push each element to the other side of the range.
Yeah, yeah,
So
like, yeah,
why we are doing that actually? I want to ask that.
okay. Okay, like in this example, what I showed when we had 6, 8, 9, 10. Okay,
Yes, sir.
your G was 5. I took modulo, it was 1, 3, 4, 0. Okay, I
Hmm.
sorted them, it is 0, 3, 4. So if you take this, your range would be 4.
Yes, sir.
But actually, if you increment this 1 and 3 and make them 5 and 6, here your range is 6 minus 3, 3. So that is less than 4. So 3 is your actual answer. You can make the range get reduced to 3 by doing this. But if you directly take this, your answer would be 4. So to get the best answer, you would have to rotate it.
So, but this is not intuitive, I think.
This is intuitive. Why? Because like if you have some range, okay,
Yes, sir.
let's say there is, this is 0, this is G basically. So you got all the numbers in this range. Okay, now let's say there is some point which is close to this 0, some point which is close to this. There are only two values. One is close to this, one is close to this. Your range would be this big, but if you increment this value here and take it here instead of here, your range would become small. So if you have only two values, one is towards this G, one is towards this G, always you can jump to the next range. So in the cross range, if you have, so this
Can
is
I ask a doubt?
smaller. Yeah.
Like you said that a plus an plus bn plus x mod GCD of AB is constant.
Uh,
Like yeah,
this thing, no?
yes. So what is the intuition here? Like, can you prove why it is constant on this?
Okay. So the first that I explained, that I first assumed that if A and B were equal, we had only one type of operation, then how can I solve the problem? That was very intuitive by taking modulo A. So that I got to the approach for that. But now the problem was that A and B were not equal. We had two types of option, either a plus A or a
Okay,
plus B.
so your complex interest fine.
Now,
Thank you.
okay, 1 minute. Let me explain this. Whoever is talking. So
Yes.
now,
Or my name.
uh, please mute whoever is talking.
Okay.
Okay. Now we had plus A and plus B. So now what the thing was, why uh, in my initial approach, why I said that this I can do take a mod A and solve the problem was because whatever value I have, if I have X, if I only can do a plus A, I can always reach X plus any only, and my mod A would always be constant. It was satisfying this property. That's why I was able to solve the problem. Now, when I have A and B both, my final value would be something like this. If I, it would be something like this. Now I need to find out how can I just make, I need to reduce the range. So how can I make them fall into a small range? So I can always use only A and make them fall in the range of A. I can always use only B and make them fall in the range of B. But with both of them together, I can obviously minimize the value. Something less than A and less than B can also be achieved. So what that less than thing would be that like I have solved a few more problems related to this, something like this. Through that, I just got the intuition that if you can do a plus A and plus B, and you need to obtain a final integer where you can do sometimes A, sometimes B, then basically what you are doing is you are moving in multiples of GCD of A and B. And why that? The proof I have explained that if I take the GCD of A and B, the GCD is such a number that I can write A as some multiple of that GCD and B as some other multiple of GCD. G is the greatest such number so that I can write both A and B like this. This is what GCD is, that greatest common factor. So it means A is a multiple of G, both A and B are multiples of G, and they are some different multiples of G. So if I can write A as some multiple of G and B as some multiple of G, this thing got reduced to this. I replaced A with
So,
this and B with this. So basically, this is some multiple of G, both are some multiple of G. So they, in modulo G, they both become 0, and I obtain X, and this X would remain constant. So by doing this plus A and plus B, basically, I can always say that if I do plus A or plus B, the GCD of A and B is the thing that modulo that would always remain constant. So this
so,
was
so, ba-
equivalent to doing the, yeah.
so
So
basically, you are saying we have to like minimize the intervals. So, like if we just take the GCD, we will just get the minimal interval which you are talking about, like the G,
Uh,
so
yeah,
that
like
we can look bit between it because G
yeah,
is the minimum we
basically,
can get.
yeah, basically my aim was to minimize the values. So I can always get it less than A by just using A operations. I can always get it less than B by using only B operations. But if I have both the operations, I can get something combined less than A and B both. So that's why I had to think of something, some less number. Like in the first test case, there was 2 and 3. A was 2 and B was 3.
Yeah,
Like
got it.
if the GCD is 1, you can just make any number basically, and you can make all of them number equals, all of the numbers equal, and you can have 0 as your final answer, because GCD of A and B became 1. And if you take modulo 1, it would be 0. So all the values would become 0. It just means you can make all the values equal. So just by looking at the test cases, like if you just look at the test cases, then also you can maybe get this intuition. Right. So like in this test case, if you look, you had 12 and 18. So their GCD was 6. So you can reduce them by 6. So here the numbers are small. Yeah, in this test case, you can see here, here A and B were 15, 19. So GCD was 3 here. So this 195, by just using 15, I could have reduced the range. Mod 15 was 9 minus 1, 8 would only remain my range. By just using operations of 9, I could reduce my range to maybe this 9 becomes 0, then maybe 5 minus 0 was 5. That's the minimum I can get. But by using a combination of both 15 and 9, I can maybe make it something less than this 8 and 5 also. So the combination of this 15 and 9, GCD was 3. So I can take, how I got the intuition is, if you have 1 plus 15, 16, 9, 9, 18, and this 9, let's say 14. So here you can reduce it to a range of 4, which is less than 5. So by doing something, you can always reduce it less than just A or just B. So what was that smaller value? So that smaller value was basically through GCD of 15 and 9, because the GCD of 15 and 9 is 3. So I can make all the values fall in a smaller range of 3. I can make the answer less than 3. So how in this case I would make it less than 3? So now I know where I have to reach. I have to reach mod 3. So for all these three values, my mod 3 was 0. Uh, Mod 3 was 0 in this case. So I can actually make all of them equal, that I know. Now, how can I make them equal? Using 15 and 9. So just you can think how you can make equal, but you can do it, that I can say. So maybe you can make 15 plus 15, 30. 999. You can make this you can make this 45 by using 3 times 9, 4 times 9. You can make it 45. You can again use 15 here and make this also 45. And this value you can do a 9, 9, 18 and 3, 45 and 3. Maybe you can do 60 here. So 3 times 9 would be 27. And so it would become 30. And then a 15. Yeah, you can make it 45. So 3 plus 9 plus 9 plus 9, that would become 30. And then plus 15, you can make it 45. So you can make all the values equal to 45 here. You can see in 3, you would perform 9 3 times, and 15 one time, you made 45. In 15, you perform 15 2 times, plus 15 plus 15, you made it 45. And in 9, you performed plus 9 4 times to make it 45. Okay, so you can make all of the values equal to 45 and reduce the range to 0. So basically, why? Because the GCD of 15 and 9 was 3. So you can make all of them. The mod 3 would be the thing that you cannot change, because if there was some 10, you and this mod 3 is 1, so it would always remain 1. That is the thing that we cannot change. So then you cannot reduce the range to less than 1. 1 would be your final answer. But if mod 3 of all of them were 0, you can make them equal. Okay, I hope it is clear now. Yeah, this problem was a little intuitive. You can say this GCD thing is not very easy to maybe get how, why. Like
So
if you solve
can
more
you
number
please
theory problems.
so
Yeah,
can you please
yeah, I'm
explain
showing you the code.
why only GCD works but not any other factor? Like if the GCD is like 20, so why wouldn't 10 would work?
Yeah, so the proof for that is basically like, uh, if this is 30 and 60, your GCD is 20. Okay, now yours, sorry, your GCD is, here it is 10. Let's say it is 40 and 60. Your GCD is 20. So here you are saying, why would 10 not work? If you imagine why I cannot make it in the range of tens, is
Yes,
because
sir. Got it, sir.
here, yeah, so here the GCD is 20. It means you can move in the steps of 20. But if you want to move in the step of 10, how can you move in the step of 10? You need to like think. So if you want to move in the step of 20, you can do a plus 60 and a minus 40. That way you can do 20. This minus 40 is equivalent to doing a plus 60 to the value to which I want to do a minus 40. Sorry, this is equivalent to doing plus 40 to all the other values. So through A, you can do plus A and plus B are the operations given to you. But effectively, you can also do minus A and minus B. How? If you want to do minus A, just do a plus A to all other values. That is same as doing a minus A to that value. So that way you can say you can always do plus minus A and plus minus B to the values. Now, if you can do this, so that means if you want to do something plus X, this X should be a combination of n1 times A and n2 times B. This can be either positive or negative. So this, if you want to do a plus X to your value, it means this X can be done. If you here you wanted to do plus 20, that can be done through 60 minus 40. So if you can write A and B, if you can write n1 times A plus n2 times B, where n1 and n2 can also be positive or negative, any integers, positive or negative. That means through A and B, if you can form this X through A and B, then you can do a plus X. But if you have 40 and 60, can you form a 10 using just 40 and 60? If you can form a 10 using just 40 and 60, then you can do a plus 10. But here, if you try, you can not form 10 just using, if you do 60 plus 60, it would be 120. Like 60 minus 40 is 20, but like you can try your combinations, but you can, the minimum value that you can do is GCD of both of them, which is 20. You cannot do 10 by just using 40 and 60. Let's say you take 4 times 60, it is 240, and 5 times 40. So it's 240 minus 200, it would be 40 still. If you take one more 40, it would be 0. But you cannot get 10 by just using 60 and 40. That's why GCD is the minimum number that you can get by just using 40 and 60. It is like a property. If you have just A and B, using A and B, the minimum number you can get, the steps of whom you can get, is GCD of A and B. You cannot get lower than that by just using A and B, because both A and B are multiples of G. You cannot break them. Okay. I hope it is clear now.
Yes, sir.
Okay, so now maybe we can move to the next problem if anybody don't have any other doubt. Okay, sorry, I had to show the code also. Yeah, so the code is simple. You took G as the GCD of A and B. Now you just assume that you can do operations of plus G. Now, if you can do only operations of plus G, what you need to do, just while input only, I'm just making modulo G. I'm making all the values to be the remainder on with G. Now I sorted all the values. Okay. So then what I did, my initial answer is, if I keep them like that, it would be the last value minus first value. That's my range. Now what I started to do, I started to rotate the values. Now while rotating the values, what I can say is, if I like I showed, if I had this 0, 1, 2, 4. So one range was 4 minus 0. Now after rotating, this 0 became 0 plus 5, which is 5. So this was my new range, 5 minus 1, 4. Okay. Now after the next rotation, this 1 became 6. So this was my new range, 6 minus 2, 4. After this became 7, this was my new range, 7 minus 4. So basically, take the initial range, which is A of n minus 1 minus A0. This is the first range. Then after every iteration, you can say that AI. So if you are taking this range, this AI plus A, or this is C, the name of the array is C. So this CI minus 1, the previous value, plus C is the maximum value now, minus CI. So this thing is the new range after the I minus 1th value is moved to, I do a plus C to the I minus 1th value, its value would become ci minus 1 plus g. Okay, so g was the range through which we were moving, the steps through which we were moving. So this once this ci minus 1 value is moved to the other side, this would become my new maximum value minus this current value. So after every rotation, this would be the value. So I took my initial answer and minimized it with all the rotated answers. Okay, through a loop. So now my final answer is my answer. So I hope the problem, the logic, and the code,
So can
everything
you
is
please
clear.
explain the rotation of answers once more?
Yeah, so let me explain it again. So if you had initially this 0, 1, 2, and 4, okay, so this is my array C. These are my indexes. So my first answer was 4 minus 0 was my first answer. So initial answer in the answer array, I stored C of n minus 1, which is C3 minus C0. Okay, so it was 4 minus 0, which was 4. Okay, now once I rotate this 0 and make it, I would add a plus g to this. Okay, so once I add a plus 5, so let's assume my g was 5 here. So it became 5. Now what is my new range? This in my sorted order, this 5 would be the new maximum and my new minimum is 1.
Yes, sir.
So
Got it, sir. Yes, sir.
so basically it is ci minus 1, the previous value, plus g is my new maximum and the minimum is ci. Okay, so this
Yes,
is
sir.
my
Thank
rotation.
you.
Okay, I hope this problem is clear to everyone. Nobody has any other doubts. So we can move to problem D now.
Can you explain the previous element logic again?
Um, it's the same thing. Maybe you can rewatch it when it's uploaded on YouTube. I've explained it 2-3 times. Like when you are moving this 5 to this 0 to 5, this would become, this thing would be your new maximum value, and this thing would be the minimum value, because you have moved all the values from 0 to I minus 1 to the other side. And this ith value is your new maximum, and this I plus 1 value is your new this is your minimum, and this is your maximum. So this ci minus 1 plus g is your maximum, this is your minimum. So that this would be your range. I hope and that is clear now. Okay, I think we can move to problem D now. So in problem D, we have been given a tree basically. So let's explain the problem. So instead of reading the problem statements, I'll explain it here only. Okay. So what we are given here is, in this problem, we are given a tree. So let's suppose this is the tree that we are given. So along with the tree, we are also given one more information, that this tree, for every node, that value of the every node is either 0 or 1. So here the green represents 1 and white represents 0. So basically the values here is, it is 1 0 0 1 1 1 0 0. Now what we are told, that for every leaf node, the you need to compute the score of this tree, and the score is computed like this, that for every leaf node, every leaf would have some value. The value of the leaf node is formed like this. So if you need to form the value for this leaf node, start from the root, go to the leaf, whatever values you obtained, this 1 0 0, write them. So while going from the root to this leaf, you obtained a 1 0 and 0. So you wrote them 1 0 0. You would get a binary string here. Now in this string, you need to check the number of occurrences of 1 0 and number of occurrences of 0 1. These two substrings you need to count and take the difference of them. So here in this case, number of occurrences of 1 0, this is a 1 0 and no other 1 0. And 0 1, there is no 0 1. So number of occurrences of 1 0 here was 1, and 0 1, number of occurrences of this substring was 0 here. So the difference of the two was 1. So 1 minus 0 was 1. You take the difference of the two. This is 1. So for this leaf node, you would say for this leaf node, the score of this leaf node is 1. The value of this leaf node is 1, or whatever you need to say. Now, compute the value for this leaf node. Here your string would be 1. Your string would be 1, 0, 1. So string is 1, 0, 1. Now, occurrences of 1, 0 is 1. 0, 1 is also 1. Difference between the two is 0. So you would say the value of this leaf node would be 0. Now, for this leaf node, it's 1, 0, 1, 1, 0. So it's 1, 0, 1, 1, 0. So here occurrences of 1, 0 is this and this 2 times, and 0, 1 is this 1 time. So 2 minus 1, the difference is 1. So the value of this leaf node is 1. And same way the value of this leaf node would be, it is 1, 0. Occurrence of 1, 0 is 1, 0, 1 is 0. So 1 minus 0 is 1. So this is 1. So the final score of your tree is the sum of the scores. Sorry, the final score of the tree is that number of non-zero values of the leaves. So number of leaves having non-zero value is your final score. So this leaf has a non-zero value, this has 0, this has non-zero, this has non-zero. So here there are 3 leaf nodes that have non-zero value. So the score of the tree would be 3. This is the final score of this tree. So that is what is explained here. So here it's these things is explained. So uh, this is how you compute the score of a tree. For every leaf node, you count, you take the string on going from root to that leaf node and count the occurrences of 0, 1 and 1, 0. Take the difference of the number of occurrences of 0, 1, 1, 0. If that difference is non-zero, then add a +1 to your answer, to your score. Okay, so number of non-zero leaves, that would be your the score of the tree. Number of leaves with non-zero weight. Okay, so now the question is, so this is not the question, this was the initial explanation. The question is that you are given a tree. In the tree, for some of the nodes, you are given the values that the value is 1 or 0. But for some of the nodes, you are given a question mark that you don't know its value can be either 0 or 1. Now you are given this initial tree with some 1, 0, or there may be some question marks which can take either 0 or 1. Now there are 2 players, Dora and Iris. So Iris would start first and they would one by one fill up those question marks. So any question mark can be filled up with either a 0 or a 1. So Iris would start first and they would fill up the question marks. Now they would fill up in such a way that so the game would continue until there are no question marks left. So one by one, the question marks would be filled up and the game would end when there are no question marks left. And the final tree that is obtained after filling those up, the score of that is what Iris would aim to maximize that final score and Dora would aim to minimize that final score. Now, if both of them play optimally, what is the final score that you need to determine? That is the problem statement. So if you take this test case and understand it. So here the tree is given, it's always given the tree is always rooted at 1 and it is a tree. So now these are the edges of the tree that we are given. So let's form the tree. So 1 connected with 2, 1 connected with 3, 2 connected with 4, and 2 connected with 5. This is a tree and this string represents the initial value. So let's say for 1 it is question mark, for 2 it is 1, then again question mark for 3, for 4 it is 0, for 5 it is 1. So this is the tree that you are given as an input. You need to find the final value, final score of the tree if Iris and Dora play optimally, where Iris would aim to maximize the score and Dora would aim to minimize the score. So if both of them play optimally, what's the final score? Now let's see what we can do. So here one possibility is let's say Iris goes first, and let's say Iris changes this. So let's form the what all leaves we have. This is one leaf, this is one leaf, this is one leaf. These are the three leaves. So your final score is basically the leaves having non-zero weights. So uh, Iris would try to maximize the score. It means Iris would try to make the leaf have non-zero weight, and Dora would try to make the leaf have zero weight. Zero weight means number of occurrences of 0, 1 is equal to number of occurrences of 1, 0. If the number of occurrences of this and this are equal, then it would have a zero weight. So Dora would try to do this thing. Dora would try to make them equal, and Iris would try to make them unequal. That's what both of them would try to do. So number of leaves that would be unequal, the count of that would be your final answer. Now Iris is going first. You would try to make it unequal. Let's see. Let's write the string for all of the leaf nodes. So for this leaf node, my string is question mark 1, 0. For this leaf node, it is question mark 1, 1. For this leaf node, it is question mark, question. Now, you can replace these two question marks. So there would be like only Iris would make a move, and then Dora would make a move. Sorry. So if Iris makes a move and replaces this, so you can see if you want to make it 0, 1 and 1, 0. Okay, let's just see if Iris replaces this question mark with 1, and then this question mark would become 1, and this question mark would become 1. This would become 1. Now here 1, 0 is occurring one time, 0, 1 is not occurring. So it is unequal case. Here there is no 1, 0, there is no 0. So this is equal case. Here this question mark, be it 0 or be it 1, if it is 0, it would be 1, 0. Okay, so if it is 0, if Dora replaces it with 0, it would become 1, 0, and they would become unequal. And if Dora replaces it with 1, it would become 1, 1, and there would be no 1, 0, no 0, 0. So it would become equal. So what is Dora trying to do? He is trying to make it equal. So he would replace it with 1 so that they become equal. Now, so that they become equal. Yeah. So your final answer is number of unequal. So there is only one unequal. So 1 is your final answer. So if at the beginning, Iris replaces this question mark with a 1, then your final answer would be 1. If at the beginning, Iris had replaced it with 0, then what would happen? This would be 0, this would be 0, this would be 0. So here 0, 1 and 1, 0, they are equal. But this is 0, 1 and no 1, 0. So this is unequal. And here, if it was 0, Dora would replace it with 0 and make them equal. So again, only one unequal would be there. So your answer would be 1. So in both, you can see in both of the cases, your final answer was 1. So in optimal play, the answer for this third test case is 1. Okay. So I hope the problem is clear. Now, the thing is that how can we check what is optimal play and all. So before doing that, let's understand how we are calculating the score. Let's try to simplify this score calculation, because if the score calculation is obtaining a string and then checking the occurrences of 1, 0 and 0, 1, and then for every question mark, you would have to determine that how can we, like, if he picks a 1 or a 0, there can be like many cases, like it would look like an impossible thing to determine initially. But if you simplify this score calculation, if you try to simplify this, then you would understand the problem becomes a lot easy. So what we can do here is we need to the weight is number of occurrences of 0, 1 minus number of occurrences of 1, 0. So what is this thing? Okay, if you try to take a look at this for any binary string, if you are given some binary string, let's say some 0, 0, 1, 0, 0, 1, 0, 1. Okay, let's say you have some binary string you need to find the number of occurrences of 0, 1 and the number of occurrences of 1, 0. What would that be? So when would 0, 1 occur? So when you have a 0 and you transition to a 1, a 0, 1 would occur. Now you have 1, 1, 1, 0. Then a 0, 1, a 0, 1. So this would be the number of transitions from 0 to 1. That would be the count. And this 1, 0 is number of transitions from 1 to 0. That's what it is. So if in the binary string, if you start with a 0, then next you can have a 0, 1. You can not have a 1, 0 if you start with 0, because you would require a 1. So until and unless you get a 1, you would not have a 1, 0. So if your string is starting from 0, then you are sure that next, whenever you make a transition to a 1, you would get a +1 to 0, 1. Okay. Now, once you are at 1, then you can do a +1 to 1, 0 whenever you transition to a 0. So in between that, you can have many ones. But only when you transition to a 0, then in between, if you have several ones, these are 1, 1, 1, 1, they have, that is neither 0, 1 nor 1, 0. So you can just compress them into a single one. You can assume this is a single one. So number of times you have ones, so you can just compress this array and assume it 0, and then all these 1 together, all these 0 together, this 1 together, 0 together, 1. So it would, if you compress these all ones together and zeros together, it would become a 0, 1, 0, 1, 0, 1, something like that. So now you have if you look at this, you can only have 4 cases here. You can either have starting with 0, ending with 1. So 0, 1, 0, 1. Starting with 0, ending with 0. Starting with 1, ending with 0. Starting with 1, ending with 1. These are the only 4 cases you can have. Now, if you see in the first case, if you make a transition from a 0 to 1 and then 1 to 0, 0 to 1, 1, what is the difference between the number of transitions? The net difference is 1 transition from 0 to 1. Then, like, if you see this 0, 1, 0, 1, 0, let's say it is this. So 0, 1, 0, 1, 0, 3 times 0, 1, 1, 0, 1, 0, 2 times 1, 0. The net difference is 1. So you can just assume this transition from 0, 1 to 1, 0, net, it is the same. It's same as if it was just 0. And if you make a transition from 0, 1 to 1, 0, the net is the same. So basically, only the first and last value matters. If you start with a 0 and make a transition to 1, there is 1 transition from 0 to 1. If you start with 0 and end up at 0, the number of transitions from 0 to 1 is same as number of transitions from 1 to 0. So the difference would be 0. Here, the number of transitions from 1 to 0 would be 1 more. So difference would be -1. So 0, 1 would be less and 1, 0 would be 1 greater. And here again, it would be 0. So when do you get a non-zero value? When your starting and ending values are different, then only you would get a non-zero value. If you start with the same value and end at the same value, then basically the number of transitions from 0 to 1 would be same as number of transitions from 1 to 0. It is like, you can say, from this you can surely say that the difference between the number of transitions from 0 to 1 is going to be same as the difference as the number of transitions from 1 to 0 if you start and end at the same value. So basically, what you can say, for every leaf, the weight of the leaf, for the weight of the leaf, only things that matter is the starting value, that is the root, and the value of the leaf. The intermediate values doesn't matter here. So if you simplify this problem like this, then this problem becomes a bit easier to solve now. That for every leaf node, you only need to consider the value of that leaf node and the value of the root node. Okay, now once you have simplified this, now how you can say that what is the optimal play? Okay, so for every, so you have these values. Let's say you have some leaf nodes. So Let's write the values for, let's say you have leaf 1, leaf 2, leaf 3. Let's say you have 3 leaves. Okay. Value for one of the leaves is question mark, one of the leaf is 0, one of the leaf is 1. And the value for your root node, let's write the value for your root node is, let's say 1. Now, if the value for the root node is known, it is not question mark. You can divide the problem into two cases. One where the root node is a question mark, one when it is known, 0 or 1. So when the value of the leaf node is known, then for value of the root node is known, then for every leaf node, the weight, for the weight, we only need to check the value of this leaf. If it is equal to 1, so for this leaf, the weight is for sure, these both are unequal. So in the answer, you would add a +1. That for unequal, your score, you would add a +1. And if since both of them are equal, you would add a +0 in your answer. Now for this question mark, it can either be a 0 or a 1. So for this question mark, this Dora and Iris, they would decide whether it should be a 0 or a 1. So what would Dora try? What would Iris try to do? Iris would try to maximize the answer. So he would try to make them unequal. So that way he can maximize. So if Iris gets to replace this question mark, he knows the value of the root. He would always add a +1. If Dora gets to replace this question mark, he would add a +0 to the answer. So Dora would always just make some value that is equal to 1 and try to ignore this leaf. And Iris would try to add a +1 to the answer. Now, so if the value of the root node is known, then what you can say for your final answer, just count how, let's say C1 represents the number of leaves having value 1 and C0 represents the number of leaves having value 0. And I'm telling the C question mark, I'm representing it by C2, number of leaves having question mark. Okay, so these can be the only 3 possible values for any leaf. So if the root is known, if I say the root is known, it is not question mark, either 0 or 1. Then for these leaves where the value is 1 and 0, their score is also known. Okay, you don't need to replace any question marks here. Their score would only represent on this C1 and this root value. Both of them are known, their score is known. Dora or Iris cannot change the values. So your initial score, what is already known. So if the value of this root is 1, you would say all the unequal leaves would be added to your score. So C0 would be your initial score. And if it is 0, then C1 would be your initial score. Okay, so that's your initial score. Now from the question marks, you would obtain more. Okay, more score. So if you have let's say 5 question marks are there. So one by one, Dora and Iris would take turn, Iris starting first. So Iris would try to make them unequal and add a +1 to the score. And Dora would try to remove this question mark and not add to the answer. So basically you can say half of the question marks would be replaced by Iris and you would add them to your answer, and whatever question mark Dora replaced, they would not get added to your answer. So you can say your answer is either this or this, whatever you get, either C0 or C1 depending on 1 or 0 plus C2 by 2. The seal of this you can say, because Iris is starting first. So if there are 5 question marks, Iris would take up 3 question marks. So this would be your answer when your root is already known. Okay, so when your root is known, so basically you can say if your value of the root is 1, then your answer would be C0 plus C2 by 2, seal of this. And if your root is 0, your answer would be C1 plus C2 by 2. Now, what if your root is unknown? So that's another case that we need to handle. Okay. Now, when the root is unknown, what we can do is basically the first thing would be, so if the root is unknown, let's say here only, here the root was question mark. So ignore the question marks first. For the leaves whose values are known, their score would also they, the score of all of them would depend on the value of the root. If you replace the root with 1, you are in your answer you would add C0. If you replace the question mark with 0, in your answer you would add a C1. So since Iris is starting first, let's say there the C1 is more. Let's say there are 5 leaves having value 1 and there are 2 leaves having value 2. Then what would Iris do? He is starting first. He can just directly replace this question mark with a 0 so that this 0 and 1 are unequal. You have 5, you add a +5 to your answer. Because if Dora gets the chance, he would replace it with 0 and he would replace it with 1 and add only +2 to the answer, because Dora is trying to minimize the answer. So if there is some difference in C1 and C0, what would Iris try to do? He would try to utilize his move by replacing this question mark with either 0 or 1, depending on which is greater, C0 or C1. So he would try to take the maximum of the two. Okay, that's the first thing Iris would do. Once this root is replaced, you got either +C1 or +C0 to your answer. C0 to your answer, the max of the two. Now, after this question mark is replaced, the remaining moves Dora and Iris would try to use on those leaves which are question mark. Now, since the root is already known, they can decide the question mark has to be replaced by 0 or 1. Iris would try to maximize the answers to replace it with an unequal value, and Dora would try to replace it with an equal value. So again, plus C2 by 2 would come. But here, so in this case, what you can write is you would take the maximum of C0 and C1. So Iris would, in the first move, he would replace this question mark with either 0 or 1 to maximize his answer, max of 0 or 1. Plus, in the remaining moves, half of the moves Iris would replace with a different value from the root to get your answer. But here, since Iris has already utilized his one move in doing this, so instead of taking the floor, taking the seal, sorry, here we had to take the seal of this. Here we were taking the seal of C2 by 2. So if there were 5 question marks, Iris would get 3 moves of them. But here, if this is odd, there are 5 question marks. Since Iris has already utilized one move here, he would only get 2 moves and Dora would get 3 moves. So here it would be floor of this. Okay. So this would be the answer, but there is again one small edge case that we are missing here is what if C2 and C1, C0 and C1 both are equal. So let's say there are two question marks among the leaves and there is 0 and 1, 0 and 1, 1. And the root is also a question mark. So, and then there are a few more question marks which are not either a root or a leaf. There are some intermediate nodes also which may be a question mark. So those would also need to be, some moves would also be needed there, although they would not affect your answer. So let's say there is one question mark in some intermediate move. Let's draw a tree, then you can understand better. Okay, let's say this leaf is a question mark, this is 0, this is 1, this leaf is a question mark, this leaf is a question mark, this root is a question mark. Let's say we have some tree like this. Now here, what you can say is among the leaf nodes, this, there are 2 question marks. So C2, the number of question marks are 2. Number of zeros is 1. Number of ones is 1. Okay. There is 1, 0 and 1, 1. And there are 2 question marks. Okay. Now, and the root is also a question mark. The root is also a question mark. Now, what we would do is, now what can Iris do here is, if Iris replaces this question mark with either a 0, if he replaces with 0, he would get C1. If he replaces with 1, he would get C0. But in both the cases, +1 is only going to get added to the answer. So instead of utilizing his move in replacing this question mark, uh, so if he utilizes this move by replacing this question mark, let's say if he utilizes with 1, this either C0 or C1, he would get 1 only. So no extra benefit he's getting. But after that, there would be a few more moves left for the remaining. There are 2 question marks on the leaf and 1 extra question mark remaining. So Dora would next get, let's say there is 2 more questions. So let's say there are 3 question marks. Okay, in the leaf node. Instead of 2, I'm taking 3 question marks. So if Iris utilizes his first move on the root, then for the remaining, let's say he replaces with 1. Then for these 3 leaf nodes, Dora would have 2 moves on these question marks and Iris would have only 1. Then Dora would get a move on one of the leaves. Then Iris would get a move on one of the leaf. Dora would get a move on one of the leaf. So Iris only has 1 move on the leaf. So he can only replace 1 question mark with a different value. So your final answer would be 1. And then 1 move would be remaining. That would be this extra. So that Iris can take and it would not change the answer. So that is some intermediate node. And this replacement would not change the answer. So this is of no use. So in this case, your final answer is going to be just 1 extra and plus 1 from either C0 or 1. 1 plus 1, 2 would be your final answer here. But if instead of in the initial move, instead of choosing the route, if Iris chose this intermediate route, he didn't perform because by choosing this route also, he was not getting any benefit. So instead of choosing this route, if he chooses the leaf, any leaf node, then what would Dora do? He would replace the root with some value so that he can minimize the answer. So that is not beneficial. So he can, instead of choosing this root, if he chooses this leaf node, that is, he is not making any change to the game, but rather just saying that, let's suppose if Dora starts first. So by replacing this question mark in the first move, instead of choosing the root node, if he chooses the intermediate node, then Dora would have to then choose either the root node or some leaf node. If he chooses the leaf node before, then Iris can replace the root node accordingly to make that leaf node unequal. So choosing a leaf node before a root node is never beneficial because the root node finally governs your final answer. So basically, if he chooses any intermediate node, Dora would then choose the root node, and choosing the root node, either of them he chooses, this one is only going to get added to the answer. Then there would be 3 question marks remaining. Iris can have 2 moves on them. So basically here it was 1 plus 1 here. Now this 1 would anyways come, but now Iris gets 2 moves among those 3. Now you have seal of basically C2 by 2 instead of floor by choosing an intermediate node at the starting. So this thing would only happen when this C0 was equal to C1. If they were unequal, then there is some benefit by choosing the nodes, root node. So the game would always start with Iris choosing the root node. But if they are equal, then choosing the root node would not change your answer. So they would first try to give the chance to the opponent. So again, if there were 2 intermediate nodes here, if this was also question mark, then Dora would also choose an intermediate node and give the chance to Iris, and it would become floor. So the number of intermediate node. So with CNT, I am representing the number of intermediate question mark. Okay. So if that is odd, sorry. So if this is odd, so if this thing is odd and C0 is equal to C1, this is the only small edge case where your answer would not be this, but your answer would be like max of C0, C1 you write, or both of them are equal. You can write any one of them plus seal of C2 by 2 instead of floor. So this small edge case you need to handle in your final here when the root is question mark. Okay. So if the root is question mark, just check that condition that I wrote there, else this. Okay. So it is root, seal or floor that we have to check. So I hope the logic is clear so we can look at the code. Okay. So
So can you repeat once the part of like transitioning if the starting and ending is 1 1, then how it's always 0 means any proof certainty.
okay, like if the initial and final values are same, then the difference between 0, 1 and 1, 0 is also same. So,
Yeah.
uh, so that's what I was explaining here is that if you have, if let's suppose you're starting with 0 and ending with 0, in between you have some 0, 1, 1, 0, something, something. Okay. But what would be the count of 0, 1? That would be the number of transitions from 0 to 1. So if you have a 0, if you start with 0, at some point you transition to 1. Now you are taking the difference between 0, 1 and 1, 0. So if you transition to 1, finally you know you have to come back to 0. So if there is a transition from 0, 1, definitely there would be a transition from 1 to 0. So they would cancel each other out. Now, if again you transition from 0, uh, from 1 to 0, and then again there is some 0, if there is a transition of 0, 1, there would be a transition of 1, 0. So if the starting point is 0 and ending point is 0, then either you can have all zeros here, then the number of 0, 1 is 0, and number of 1, 0 is 0, or you can have at some point a 1, then a 0, then a 1, then a 0, something like that. So a transition from 0, 1 would means C0, 1. So how many transitions from 0, 1 is 1 and 2? If you have a transition from 0, 1, for that correspondingly, you would have a transition from 1, 0. For a transition of 0, 1, you would correspondingly have a transition of 0. So they would always cancel each other out. You can understand. So if you are starting with 0, at any point to transition to 1, you would have to come back to 0 at some point if your final value is 0. If you again transition to 1, you would have to come back to 0. So for every 0, 1, you would surely have a 1, 0. So that's why if you're starting with 0 and ending with 0, the number of 0, 1 and number of 1, 0, this count would always be same. Same way if you are starting with 1 and ending with 1, the number of transitions from 1 to 0 would cancel out the transitions from 0 to 1. 1 to 0, then 0 to 1. Okay.
Got it,
I
got
hope
it, sir.
it is
Yes, sir.
clear now. Yeah. And when you have them unequal, then if it is 0, 1, there would be one transition from 0 to 1. And after that, the other transitions would cancel. If it is 1, 0, there would be a transition from 1 to 0, and the others would cancel each other out. So I hope it is clear now. Okay. So now in the code, one more thing, like if you get these things, so for the code, what all things we needed? Like this was the final my answer basically. Here there was one more condition that I wrote there, that if that condition is satisfied, then that, otherwise an else part here. So that separate condition I wrote here. So my final, basically for my final answer, I can write this if else, but for this I would need some C0, C2, C1, and this CNT. These four things we need. So first we would have to compute this C0, C1, C2, CNT. So what all these are? These are number of leaves having 0. This is number of leaves having 1. This is number of leaves having question mark. And this is number of intermediate nodes having question mark, and the value of root node also. So whether root node is a question mark or 0 or 1. So if we can calculate these values initially, then we can write our final answer. Now, how can we calculate these values? So first thing is, what would be the value of the root node? Root is always 1. So the S0, if I'm taking 0 based indexing of my initial input string, S0 would represent my root node. So that I can obviously get directly. Okay, now what would be C0? So we would have to check what all are the leaf nodes. So for the input, what we would do, we are given the input in the form of nodes UV. So just form the adjacency list of that tree basically. And for every node, for every I, just check if that is a leaf node. If it has no children, it is a leaf node. Then if that is a leaf node and the leaf node has a value 0, add plus to C0 accordingly. You can add a plus plus according to 0, 1 or question mark. And for this CNT, for other nodes which are not leaf node, if that is a question mark, add a plus to your CNT. So in the code, you can see what I did. I took the input. So I took and the other nodes. If the size of the adjacency list is 1, it means it only has a one single parent and there is no child of that. Then I would say that it is a leaf node. And if this is a leaf node, so S of I minus 1, because here I have taken 1 based indexing for my adjacency list, and my string S has 0 based indexing. That's why I'm just converting from 1 to 0 to check. So this I is from 1 to N, but my string indexes of my string is from 0 to N minus 1. So that's why I'm taking S of I minus 1. If that is a question mark, add C2 plus plus. If that is a 0, add C0 plus 1 plus plus, else C1 plus plus. So for the case of leaf node, this is what I am doing. And for the intermediate nodes, like here also you can do in the else part, you can write if it is question mark, add CNT plus plus, or what I did, I took the total number of question marks minus C2, the number of question marks which are leaf node, minus if my root node is a question mark. So for the all the question marks that I have, if I subtract the question marks from the leaf node and the root node, I would get the question marks in the intermediate nodes. So this way I've calculated my CNT. Once I've calculated all these values, I can just write the thing that I wrote there. If my root is a question mark, then what I can say that if my root is not a question mark, so for the first case, if my root is not a question mark, if it is either 0 or 1. So if it is 1, I would take C0. If it is 0, I would take C1. So if my root is 0, I took C1, else I took C0 as my answer. And in the answer, I added the seal of C2 by 2. And to calculate the seal of C2 by 2, I can write C2 plus 1 by 2 because this division is an integer division for two integers. So if it would be odd and I do plus 1 by 2, it would give me the seal. So, and I see out my answer. Now, when this S0 is a question mark in the else part, then again, I would check this edge condition. If my CNT is odd and C0 and C1 are equal. So if C1 is equal to C0 and my CNT is odd, then I would add the seal of that to my answer. Otherwise, the floor of that to my answer. And my initial answer was max of C1, C0. Okay. So I hope the code is clear now. And the problem is also clear. So if this is clear, we can move to the next problem now. Okay, I think we can move to the problem E now. So problem E, you are given a rooted tree with the root at vertex 1. Okay, again you are given a rooted tree with root at vertex 1. But this problem is a little different. So what we are given here is that there's an edge connecting what okay, so you are given a tree here. Now every edge has some weight. This ti represents the weight of that edge. Okay, and the sum of weights for all the edge is w. This is what we are given. So we are given a rooted tree rooted at 1, and it is a weighted tree. Every edge has a weight, and that weight is some ti, and the sum of weights for all the edges is w. Now, and every it is a non negative weight. So there is no negative weights here, only positive weights. The vertices of the tree are numbered in a special way. The numbers of the vertices in each subtree are consecutive integers. In other words, so one more property of this tree is given, that they are numbered with consecutive integers. So if you perform a DFS traversal in this, you can get consecutive integers. So here, if you look at this tree, uh, okay, like if you look at this tree, if you perform a DFS traversal, you can get 1, 2, 3, 4, 5 here. How? 1, 2, 3, 4, then backtrack to 5, then to 6. This way you can get 1, 2, 3, 4, 5, 6 as your like pre-order traversal would be always consecutive integers. So in this tree, there would always be a way to get, so this is in such a way so that uh, you would get a pre-order having consecutive numbers from 1 to n. So basically, if you 1 is the root, after that you would have a 2 as its intermediate immediate child, and for 2, if it has some child, it would have 3 as its child. If 3 has some child, it would have 4. After that, if 4 doesn't have a child, then when you backtrack and go to the next node, it would be 5. So basically, there would always be a pre-order traversal so that it gives 1 to n as your uh, traversal order. So you are given the tree in such a way. Or one more way of definition is given here, that for this 2, if you take all the subtree of this subtree would have all the consecutive values only. So this subtree had 3, 4, 5. So they were consecutive values. So this is okay. So for every node, if you take the values in its child subtree, then that subtree would have consecutive values. It won't be 3, 4, and 6. If it is something like this, that's not a valid tree. So if you look at this tree, for this, okay, I think this was the thing given for not, for example, subtree of vertex 2. Yeah. So if you look at the subtree of this vertex 2, there is 2 comma 4 in this subtree. There's no 3. So this is not in consecutive order. So this is not a valid tree for the question. So you are in the question, you are always given a tree where you in the DFS order, you can get consecutive integers. So this is already given to you. Don't need to check whether it exists or not. You are given a tree like that only. Now we define distance UV as the length of the simple path between U and V in the tree. So if this is U and this is V, so the length of a simple path from U to V is defined as the distance UV. So from U to V, a simple path is this. So it has 1, 2, 3 nodes here, or you would consider the weights of the node. So you are given the weights of the node, the sum of the weights of the edges, sorry, the weights of the edges. The sum of the weights of the edges on the simple path from U to V is called the distance of U to V. Okay. Now next, there will be n minus 1 events. Iris is given x and y, indicating tx is y. So there, for a tree of n nodes, there would be n minus 1 edges. So basically, initially, what it says that you are not given this weights of the edges. Initially, you are only given W, that the sum of the weights of the edges is W, but those exact weights are unknown to you. Now, one by one, you are given the weights of every edge. So first you are, so like 2, 4, 3, these you are given one by one, the weights of these edges are revealed. Now, what you need to do is, after each event. So after every event, you are given this X and Y, which represents that TX is Y. So it means the edge to the parent of X. Basically, if X is 2, so if X is X equal to 2, you are given, it represents this node. The node just, the edge just above 2. So for every node, there would be only one parent. So the edge connecting that I with the parent of I, that edge is represented by this I. Okay. So this X represents, say, if this X is 2, it represents this edge. And if it is Y, it means the weight of the edge is Y. So this is how you are given the information. So one by one, you are given the weights for all the nodes. Now, one by one, they are giving the weights and you need to compute. So one by one only you need to compute when the first weight is given. After that, maximum possible value of distance I modern plus one independently for each I. So basically what it says, I'll show you. So let's take the first, let's take this test case only. So, okay, let's take this only. Okay, so here you are given this test case, let's say. So what does that represents? One is the root node, and then these, uh, okay, are you given this? Yeah. So this is the parent array to represent the node. So parent array just means it represents the parents of every node from 2 to n. So 2, 3, 4. It means the parent of 2 is 1. So this is how you would draw the tree. The parent of 2 is 1. So this 2 is connected to 1. The parent of 3 is also 1. So the parent of 3 is 1. The parent of 4 is 1. So this parent array, basically this parent array represents this tree. Okay, you formed a tree. Now you are being given. So initially these weights are unknown. You are only given this 9, that W is 9. It means the sum of weights for all the edges would be 9. But when you start with, you are being given the weights one by one. So when you are given this weight 2, 2, so initially these are unknown. Okay, so this is unknown, this is unknown, this is unknown. You don't know the weight. Let's name this as T2. So this as is represented by this 2. So uh, I'm giving the weight of this as T2. This T3 represents the weight of this edge. T4 represents the weight of this edge. Now you need to find out, like, after the first you are given that the edge 2, this is X, this is Y. So this edge represented by this above this 2 node X, since X is 2, the weight is given as 2. So it is giving this information that this T2 is 2. So this weight you are given that it is 2. Now after this information is given, these T3 and T4 are still unknown. With these values, you need to find the maximum value of this thing, which is distance of I comma I plus 1. So like, okay, like I'll tell you what mathematically it was written. What does that mean? Is you need to find the distance of 1, 2 plus distance of 2, 3 plus distance of 3, 4 plus distance of 4, 1. So for n equal to 4, if you have 4 nodes, you would find the distance from 1 to 2, 2 to 3, 3 to 4, and 4 back to 1. So the sum of these distances, you need to find the maximum value for this sum, because here you are only known, this is known, but these two are unknown. So you can take values for them as you wish, so that this thing is maximized. So basically, individually, you can have separate values for them. So first you would try to maximize the value for distance 1, 2. Okay, so for 1, 2, here the weight is already known. So it would be 2 only. Now for 2, 3, from 2 to 3, the weights is this T2, which is 2 plus T3. So this is actually 2 plus T3. Now you know that T3 plus T4 is the sum of the three weights was given as 9. This W was given as 9, where T2 is already 2. So T3 plus T4 is 7. So it should satisfy this condition, but you can take T3 and T4 anything. You could take 7, 0, 0, 7, anything to maximize your answer. So here, you for this case, you can take T3 as 7 to maximize your answer. So it would be 2 plus 7 equal to 9. Now for this case from 3 to 4, this both it is T3 plus T4. Now you know T3 plus T4 is 7 only, so you would have to take 7 because this is whatever combination of that you take, its sum would be 7 only. Now for 4 to 1, the path from 4 to 1 is T4. So it is actually T4, and what's the maximum value you can have is if you assign all the 7 to T4, it would be 7. So your final answer here would be this 2 plus 9 plus 7 plus 7. So 2 plus 9 plus 7 plus 7. This is going to come as 25. Okay. So after the first query, you would answer 25. Now, after the next query, you are said that just above 4, you have a weight of 4. So this T4 is replaced by 4. Now, since this T4 is known and T2 is known, only unknown is T3. So this T3 actually is also known now, that 2 plus 4 plus T3 is 9. So this T3 is going to be 3. So this T3 is also gets known now. So since all the three edges are known, your distance would be fixed. You cannot maximize, like whatever the distance, that's only the maximum distance. So here from distance from 1 to 2 is 2. Distance from 2 to 3 is 2 plus 3 here, which is 5 in this case. So it is 2 plus 5. Now distance from 3 to 4 is 3 plus 4, which is 7. Distance from 4 to 1 is 4, which is plus 4. So this value is going to come out to be 18. So this is 18. Now this 3 is known. It was already known there. So here nothing is going to change. For this test case also, it would be 18. So this is what you need to find out. I hope the problem is clear now. So what? So how can we compute this? So one way is just do the brute force thing. But there, if you look at the time complexity, you have n up to 2e5. So you have 2e5 nodes, and then you have n minus 1 queries. So in every query, if you are updating the values, and for the sum you are storing this, it would go something O of n square or greater than that, the brute force approach. So you need to find it optimally. That's the main problem here. So how can you do this is, first thing you need to notice here is this graph is given in such a way so that it's always the DFS ordering is always 1, 2, 3, 4. This is the DFS ordering. So basically, if you traverse, so what all the distances you need to calculate is from 1 to 2, 2 to 3, 3 to 4, 4 to 1. So if you are going in the DFS order, you are traveling in this way only. So basically, you are traveling from 1 to 2, then to 3, then to 4, then back to 1. So basically, if you are traversing this whole tree through a DFS order, you are traversing in this way only. Now, in the distance, you basically need to find the sum of the distance. So when you traverse from 1 to 2, just add this sum. Then from 2 to 3, this edge would appear. Then from 3 to 4, this would appear. Then 4 back to 1. This would appear. Now you can see, just let's say, what would my answer be? That would be this distance 1, 2. What I can write is distance 1, 2. This was from 1 to 2. It was T2. It was T2. Distance 2 to 3. This distance 2 to 3 was T2 plus T3. Distance 3 to 4 was T3 plus T4. and then you have distance 4 to 1, which was T4. So basically, finally, what you need to find is the sum of this. So sum of all these values you need to find. If you look at this, what is this? Here you have 2 times T4, 2 times T3. Sorry, here it was T2 plus T3, and 3 to 4 was T3, T4. 1 to 2 was actually T2, not T4. Okay, 1 to 2 was T2. So here you have 2 times T2, 2 times T3, and 2 times T4. So basically, if you just look at any tree which has this consecutive ordering, something like that, if you do the DFS traversal, complete DFS traversal, for every edge, you would travel one time while going and one time while backtracking. So every edge would be traversed 2 times. So this, your final answer is basically 2 times T2 plus T3 plus T4. So it would be 2 times the sum of weights of all the nodes. And when your all the weights are known, you know the sum of weights is W. It would be 2 times W, your final answer. Like for every test case, you can see if W was 9, your final answer was 1880. You can look here. If W was 1000, your final answer was basically 2 times W. Like 10 to the power something, your final answer was 2 into 10 to the power that. It was 9, your final answer was 18. It was 100, your final answer was 200. It was 511, your final answer was 1022. This thing you can notice. Now, this final answer is not a problem. The problem is the initial answers. These initial answers are bigger than that, because here, when you're considering the distances, they are you are finding the maximum individually, not in overall sense. So individually, when you are finding, then you can have this T3 different and this T3 different. Because when this is T2 plus T3, you can take T4 as 0 to maximize this T3. And when it is T3 plus T4, or when it is T4, you can take T4 as greater value and T3 as 0. T4 as some remaining value and T3 as 0 to maximize this. So by taking different values, you can maximize your answers. So you just need to find. So first thing you can see is whenever you replace an edge with a fixed value. Initially, all the edges, the value of all the edges was unknown. One by one, you are replacing them with a known value. And then you need to compute your answer. So initially, when all the values were unknown, what you can say? When initially, let's say before the first test case, like before the first query, when all the edges are unknown, you can just take all the sum to be equal to W. If it is distance 1, 2, you can take T2 equal to W. If it is distance 2, 3, you can take this sum as W remaining 0. You can take this sum as W remaining 0. So how many distances you need to calculate? For n node, there would be n distances, and every value would be W initially when all the weights are unknown. You would assign the nodes in the path to have a sum of weight as W and remaining nodes as 0 to get your maximum weight. So before the first query, your answer would be n into W. This would be your, let's say, your answer before the first query. Now, after every query, you need to update this answer so that it fits your conditions. Now, what all updations would be required? So, like here, your first case was replacing this T2 as 2. So after the first query, you replace this T2 as 2. Now T2 has a fixed value of 2. So here you were taking this W, you were taking 9, but now you can only take 2. So for all those, and like here also, this 2 is fixed, but this T3 is unknown. So here again, you can assign the remaining value of 7 and make it 9. Now this T3 plus T4, this would also get affected. It was 9 before, but now you know some 2 is there in T2. So this T3 plus T4 can at max have 7. So basically, initially it was this thing was actually 9999. After replacing this T2 by 2, the distance 1, 2, since it was T2, it became 2. Distance 2, 3, since it had T2, but there was some unknown T3. So this became 2 plus, for unknown you assign 7. So this remained 9. For this T3 plus T4, before all the values were unknown, so you assigned 9 to this T3 plus T4. But now you know that T2 contains 2, so the remaining value you can assign is only 7. So instead of 9, it would become 7. Again, for T4 also, the remaining value is 7. So you would assign 7. So what you can say, for the unknown values, you can assign all the remaining value. So if you have some known values, initially, if you have this known value 2, what you can do, your remaining unknown value, you can subtract it by 2. So here your remaining unknown values were 9, you made it 7. Now for all those places where there is some unknown value, you can replace them with 7. So here there was some unknown value, replace it with 7. These were unknown value, replace it with 7. Unknown value, replace it with 7. And for the known values would be replaced by the known values. So this way your answer is going to be computed. So if you can calculate this change from 9 to 2, from 9 to 9, no change, 9 to 7 change, 9 to 7 change. If you can calculate this change in some O of 1 or something, some optimally, then you can find your final answer. So basically we need to calculate the change. So what I can say is my final answer after some point, let's say after replacing some edges, after some point, there are some values that are known. So some Ti are known and there are some Tj, let's say, which are unknown. Okay. And initially you knew that summation of Ti was W. Now, when you have some known values, okay, so uh, when all of them were unknown, all of them were Tj. So summation of Tj was W. Now, when you have some known values, you can reduce the summation of. So basically, you can write the summation of Ti plus summation of Tj is W. That is for sure. That in sum of all the nodes is W. But these Ti are known, Tj are unknown. Sorry. So since this Ti is known and these are getting known one by one, you can store this in a variable, say sum. Now you know that summation of Tj. You can call this as the remaining value, which you can assign to the unknown values. That is equal to W minus sum. Okay. So basically you can maintain this remaining variable every time. These are the values that are not assigned to any nodes. These are unknown. So whenever there is some unknown value, you can assign this full remaining. Initially, when everything was unknown, this remaining was equal to W. So you assign W everywhere. What you did initially, when everything was unknown, you assign W everywhere. Now, once something is known, this W got reduced. So basically, you are assigning the remaining value, which are unknown, the sum of unknown values. That complete sum of unknown values you are assigning. So now, after 2 is subtracted, this remaining remained 7. So instead of 9, it became 7. So basically, I can say after some point, your answer is going to be for all those distances, like for all those, there are n distances that you need to calculate. Okay. Every distance is the distance between I and I plus 1. For I when it's n and 1, for it's I and 1. Let's say I'm representing this by let's say I'm representing this distance by di. Okay, di represents this distance. So basically I am telling that this thing is d1, this thing is d2, this thing is d3, this thing is d4. Okay, so this d1 is t2, this d2 is t2 plus t3, this d3 is t3 plus t4, this d4 is t4. So for every d, it is a combination of some t, a sum of edges. Now, if for this D, if both T2 and T3 are known, then the value of this is fixed. If one of them is unknown, then you can say you can assign the known values, which was 2. And for the unknown values, you can say assign it as remaining. So it was 2 plus remaining was 7. 9 was the value of D2. So you can say if you know for every DI, this DI is constituted by what all edges, then if it is constituted by some of the edges which are known, then the sum of the known edges plus remaining if there is at least one unknown edge. If there are no unknown edge, it would be only this. And if you would add plus remaining, if there is any unknown edge. Okay. Now you would have to just maintain that for every DI, what all edges constitute that DI, and among them, how many are unknown. If you can maintain the count of unknown edges in DI, if that count is greater than 0, you would add plus remaining. Otherwise, the sum of known edges, that sum also you would have to maintain in some variable. So basically, what all things I am doing, like I'll explain you better with my code, so that you will so before like moving to the code, so you would understand more with the code how I'm managing this updation thing. You just need to manage this updation thing so that you can compute your answer. You can just update your answer after every operation. So like before managing, first let's okay, like from the code only, let's see how I'm doing this. This is a little maybe difficult to explain. That's why I'm trying to explain you through the one by one through the code only, what I'm trying to do. Okay, so first thing that I did is I took this. Okay, sorry, this is the code. The first thing I did is I created my adjacency list for my tree. So for the given tree, I run a loop from 0 to n. So I was given the parent array. So I use this parent array adjacency of pi dot pushback I. So this way I created my adjacency list for the tree. So I basically I took the input. This adj represents my adjacency list for that tree. Okay, I was given the input in form of parent array. So that's why I did it like this. I have that is clear now. So this adjacency list is taken. Now I need to move in the order of consecutive values. Basically, I am already given that this tree is in such a way that your DFS pre-order traversal would give you 1, 2, 3, 4. But maybe you may move from 1 to 3 and then to 2. That would not give me a 1, 2, 3, 4. So you would have to move in the sorted order. That's why for 1, I would always move to the lowest value first among its edges. You can move to 2 or to 3 or to 4, anyone. But if you sort them, if you move in the sorted order, then you would always have 1, 2, 3, 4 like this. So that's why after taking the input, I just sorted all the all the childs for every node, so that when I do the DFS traversal, I'm moving in sorted order, so that I'm always moving in 1, 2, 3, 4, 5 like this. So my traversal order is always from 1 to n in a sequence order, in with consecutive integers. So I sorted this. Now let's ignore this for now. Now I run my DFS. Now what I'm doing in the DFS, let's ignore this. Okay. I'm just running my DFS traversal, that for every child of the node, I'm running a DFS again. So just if you look at this function, and inside the for loop, I'm running the DFS. Let's ignore these things for now. Okay. Like if you look at this function, what is this? This is the DFS, simple DFS traversal of my tree. And in this DFS order, since I've sorted this, and in the question I'm given that I'm always moving in consecutive order, that I am sure whenever I'm calling this function, I'm calling this in the order of 1, 2, 3, 4, 5, 6 up to n. So in this X, the first time the this function is called, it would be called for 1, then for 2, then for 3, then for 4, then for 5. That way it would be called. This I am making sure. Now, what I need to do is I'm going to maintain like what I need to find. I need to find this thing now. That for every distance, this D1 distance is constituted of what all things, what all edges. This D2 distance is constituted of what all edges. This D3 is constituted of what all edges. I need to maintain that thing. So, and along with that, so for my final answer calculation, I need to maintain that thing. And like in that thing for DI, more specifically, what I need to maintain is the sum of known edges, sum of weights of the known edges, and the number of edges that are unknown. So what I did, I created two vectors. One was unknown n. So this is one array. What it represents, that unknown I represents that number of edges which are unknown in uh, di. Okay. So my unknown I represents the number of edges which are unknown in di, where di is my distance from I to I plus 1. Okay, like in my code, it di was I minus 1 to I. Okay, like in my code, I have taken this as, this is D2, this is D3, this is D4, and this is D1. Okay, I've taken it through the second values. Okay, it would remain the same thing. You can take it I and I plus 1. So my di is the distance between I minus 1 and I node. Okay, this is my di. Now, my unknown I represents number of edges unknown in di. Okay, so this di is constituted of some T2 plus T3 plus T4, something like that. It would be constituted of. Now, among them, how many edges are unknown? That is represented by unknown I. So that I would use to calculate how many are remaining. And the second thing would be the sum of the known edges. So for that, I would take here, what I am taking is B. Okay, so for calculating the sum of the known edges, what I am doing, that for updating the edges, one more thing that you can notice here, that for T2, it was falling in 2, in D3 and D2. This 2 was falling two places. Like, as I explained here, if you do the TFS traversal, every edge would be contained in two distances, one while traversing and one while backtracking. So every edge would be contained in two of the Ds. So I am storing so when I need to update an edge, I would need to know what all D I need to update. So if this T2 is getting updated, I would go to this D2 and D3 and update them. So for that, I need to know that for this T2, it belongs to which Ds. So I'm taking another vector. So this belongs to of I represents that this is a vector. This would have two values. Okay, so it represents the uh, okay, let's call it J. All I for which like you can say it like this edge J. You can say this represents this edge J is contained in which all DIs. Okay, so this would have the values of all those all those DIs for which contains this edge J. So like in this case for T2, this T2 was contained in D2 and D3. So here my belongs to of 2 would have, so belongs to of 2. It means that this T2 is contained in D2 and D3, so it would have 2 and 3. Okay, this is how I am storing the values in belongs to. That this edge 2, this T2 edge belongs to which all distances. Okay, it belongs to D2 and D3. So that's what I am storing. That's what I'm mapping in this BTO vector. So these two things I'm maintaining. So I have taken this BTO, which is a vector of vector, and this unknown. Uh, these two things. Now, how I am doing this is when I'm moving, like when I'm traversing from 1 to 2, when I'm moving from 1 to 2, I'll put all the edges that I'm traversing through in a stack so that when I move to 2, all those edges through which I came to 2 would be the edges for D2. So D2 would have T2. Now for D3, I would backtrack here. So D3 would have T2 and T3. Okay, so what I would do is I would store in a stack. Uh, I would, while traversing, whichever route I'm either traversing or backtracking, both of them I would put in a stack. So when I'm traversing this, my stack is initially emptying. When I'm traversing this, I store 2 in my stack. So because I traversed through the edge 2. Now when I move to this node 2, I just emptied this stack into my belongs to vector. Basically, that this node 2, uh, so like all the edges in this stack, all the edges in this stack, they belongs to this D2. So for, I would say that belongs to of this 2 is this D2. Okay. Now when I backtrack, so this stack would become empty. When I backtrack, again, this 2 would get into the stack. Then when I went to 3, 3 would also get added to the stack. Now my stack is 2, 3. Now when I went to 3 from 2, now this D3 would have T2 and T3. So I would say that belongs to of 2 is also D3 and belongs to of 3 is also D3. Okay, so basically what I am doing is for every distance between 2 to 3 is D3. So between traversing 2 and 3, what all edges I am traversing, these would constitute the distance D3. So that I am storing through by putting them in a stack and then emptying it when I move to a node. So what I did here is I took a stack. Before traversing, I put it, and after I have traversed, when I'm backtracking, there also I'm putting. So the edge can occur in two ways, either when I'm moving to it or when I'm backtracking through it. So in both of the time, I'm putting it into a stack, and let's ignore this if condition for now. What I'm doing, I'm emptying this stack. So all those edges that were in the stack, so for all those edges belongs to X. X is my node. So dx, basically I'm saying that all those edges belong to the distance between X and X minus 1. So dx represents distance between X and X minus 1. So all those edges belongs to the distance between X and X minus 1. So belongs to of stack dot top dot pushback X. And initially all the edges are unknown. So I'm doing unknown of X plus plus. So initially all the edges are unknown only. So I'm initially filling up this unknown vector with plus plus. The count of basically it will store the edges it has. Okay, and stack dot pop. This way I'm filling up. Now why I did X not equal to 1? Because for 1, like here, I would fill up D2, D3, D4. But for D1, this would be filled up when I have traversed till 4 and I'm backtracking to 1. So that I'm doing initially when I call DFS, it would be called for 1. So initially that there I would not store D1, but I would store it afterwards when I have finally backtracked through traverse the whole tree. There I would store unknown of 1 and push back 1. So this thing I'm doing separately. If you did I and I plus 1, if you take like this, then maybe you would not have to take it separately. But here for X equal to 1, I'm doing it outside after I have traversed this whole tree. Okay, so this way I am maintaining this unknown and belongs to vectors. Okay, once I have pre-computed them, now I would say initially before any query, my answer is my sum is storing the sum of known weights. Okay, so my sum is storing this sum of known weights for every D. Okay, so like here, this was known, so my sum would store 2. This was known, it would again store 2. So for the known weights, the contribution of the known edges, that is stored by my sum. So initially there is no known edges, so my contribution for the known edges in my sum is 0, and remaining is n. Is this is the number of distances where there is some unknown weight. Okay, this remaining is not the remaining I wrote here. Okay, this remaining is stored in W only. I'm updating my W only like that. Okay, so what the remaining in my code is basically the number of D's where there is at least one unknown. So for all those, that many times I would add W to my answer, the remaining W to my answer. Okay, so here, if you look after this 2 was assigned, this was unknown, this was unknown, this was unknown. So 3 times 7 was added to my answer. So basically, I can say once how I am computing here is once this T2 got known, I replace this D2 by 2. So in my sum, which was 0, once this T2 was known, its contribution was 2 times. So plus 2, it became 4. These two contributions are handled. And for these contributions, there are 3 Ds where there is at least one unknown. So I would say plus 3 times the remaining weight. The remaining weight is 7 now. So plus 3 times 7. So I would say my final answer is 4 plus 3 times 7, which is 25 after the first case. Because for whichever D there is at least one remaining, I can replace that remaining with the full remaining weight of unknowns. Okay, so these would be replaced by 777, and there it would be 2 2. Okay, so my final answer would be 2 2. These are known, which is stored in my sum, and 777 3 times 7, which is denoted by my remaining into W. So my final answer is sum plus remaining into W, and but I have to maintain my sum and my remaining and my W also. W is actually remaining W, not the actual W. So whenever I get a Y, I reduce my W by Y. So this is the remaining weight of unknown edges. Okay, so this is the remaining weight of my unknown edges. And for every, whenever I get a known edge, I need to compute this and this also. So whenever I get an edge X, so I would go to every, basically this belongs to vector denotes all the distances where this edge belongs to. So I'm iterating through all the distances where this edge belongs to, and my unknown J minus minus. So this is not, if it has three remaining, three unknown nodes in J, this minus minus would make sure that I have two remaining. If I have only one remaining, it becomes 0. If the number of unknowns becomes 0, then this remaining minus minus, that number of distances that have at least one remaining is now reduced. This distance, this DJ is not a distance where there is something unknown. So remaining minus minus. So that would not add a plus W to my answer. And this sum plus equal to Y, obviously. I would add a plus Y to my answer for every. The contribution is Y for this known edge. Okay, so I hope this is clear. If it is not clear, maybe you can rewatch it one more time and try to understand. This was a little complex problem to understand. Okay, so I have tried to explain the code and all the representations that I have written. I've written it here, what all things I am taking. Basically, you have to maintain these things. You have to update the answer in optimized time. So that was the main thing here. Okay, so I hope this problem is clear, so we can move to the next problem now, which is Okay, problem F, what we are given. So again, like this is an even harder problem. So in this problem, I would like try to explain the intuition first without wasting too much time. I hope if you are seeing this problem, you would be able to understand that I am expecting that much from you. Okay. So here what we are given is you are given some distinct positive integers. And then what you are said, like you are given an array basically, and what you need to do is okay, so here you are given an array and you need to find there is some definition of something called brilliant some definition of a brilliant array is given. What does that mean? That an array is called brilliant. Let's say there is 3, 6, 10. This would be called brilliant if you can perform an operation of this way. You can choose to any you first need to form a set of this. Okay, like you need to put all the elements of the array into a set, and then you can perform an operation from this set. So like if you put these elements into a set 3, 6, 10, then what you can do, you can pick any two elements of this set, take the average of two. Let's say you picked 6 and 10, take the average of 6 and 10, 6 plus 10 by 2, which is 8, and you can insert this 8 into your set. So this 8 got inserted into my set. That way you can perform the operations and insert some values into the set which were not present by taking the average of any two values which were present in the set. So by inserting like this, you need to form a set having consecutive values. So here, if it is a set of 3, 6, 8, 10, it is not consecutive. If you can perform more operations, so like if you take 6 and 8, 6 plus 8 by 2 would be 7. You inserted a 7 here. Then you took 8 plus 10 by 2, which is 9. You inserted a 9 here. Then you took 3 plus 7 by 2, which was 5. You inserted a 5 here. Then you took 3 plus 5 by 2, which was 4. You inserted a 4 here. Now your set becomes 3, 4, 5, 6, 7, 9. So now in this set, you have consecutive values only. There is no gaps in between. If you are starting with 3 and ending with 9, it means you have all values from 3 to 9. If you can, by performing the operations again and again, any number of times, if you can form a set having consecutive values, then you would say that this array is a brilliant array. Okay. Now you need to find for the given array the number of sub arrays which are brilliant. This is what the question is. So basically for this, how many sub arrays exist for an array of size n? There are n into n plus 1 by 2 sub arrays for an array of size n. Okay. So just check every sub array. If they are brilliant, add a plus 1 to your answer. That's your answer. So your brute force approach would be this is just go to every sub array, which is n into n plus 1 by 2 times. And for every sub array, this checking. If you can, in O of anything, if you can derive some wave checking, still it would be O of n square into something. And n is up to 1e5. So this would not work in any way. So you need to devise some way to count the number of subarrays without individually checking for every subarray. Okay, so let's like jump to the logic straight away. Maybe this was like I had to think a lot for this to come up to the logic, so not very easy and intuitive to think. But okay, like I'll jump to the logic. What we can do here is okay. Like first, the intuitions that I got here was the first thing you can see, like if you have a single element, that would always be brilliant. Single one would always be brilliant. A single three would always be brilliant. But if you have two values, let's say 6 and 10, when can this be brilliant? If you have two values, 6 and 10, if their difference is 4, it means you can assign a middle value 8 to them. Then with 6, 8, their difference was 2, you can assign 7, you can assign 9. If the difference is some 2 to the power n, If the difference is some 2 to the power n, you can always get all the values in the middle. By since it was 6 and 10, you got a 8 in the middle, and through these two you got 7, through these two you got 9. If it was, let's say, 6 plus 8, 14. Okay, the difference is 8. You can get in between there is 10, 6, 10, 14. Now with 6, 10, you can apply the same thing and get 7, 8, 9. Here you can apply the same thing and get 11, 12, 13, 14. So you can see if the difference between two values, if the difference is some 2 to the power n, then you can always say yes, you can form. Now for two values, if the difference is not 2 to the power n, if the difference is 6, let's suppose 2 and 8, difference was 6, you can never get all the values in the middle. You can take the middle value, which would be 5. After that, 2, 5, 8, if you perform operation in between these two, this would give you 3.5, which is not integer. You cannot perform this, which is not integer. Like here you would get 5. So anyways, you cannot proceed further. You can never get a 3, 4, 6, 7 here. So the first intuition that I got here is, for two values, if the difference is 2 to the power n, then a yes, otherwise a no. But what if there are more values? What if there are 2, 8? As I told, in 2, 8 you cannot get. But if along with 2, 8, you again have, let's say, 11 also. Or let's say 2, 8 and 13. Okay, here difference was 6, here difference is 5. Now, if this difference is also 11, there is no 2 to the power n difference. But still, if you see here, with 2 and 8, you can get 5 here. With 2 and 8, you get a 5 here. It became this. With 5 and 13, you got a difference of 8 in between 5 and 13. Now you can form all the values from 5 up to 13. And then you are remained with 2. Now, in between 2 and there would be 6, which you can form. In between 2 and 6, the difference is 4. You can form all the values. So basically, you can form all the values from 2 to 13. Although there was no difference of 2 to the power n here, but still you were able to form. So basically, what the thing here is that first is, if you have some difference which has some factor of 2. If it is 6, first erase all the factors. It is 3 into 2. Erase all the factors of 2. Because that you can obviously do. The problematic thing would be this 3. Why you cannot make a difference of 6 to have all consecutive values between if there is a difference of 6? Why you cannot make a brilliant set is because of this 3. 3 is one of the factors. If it has only 2's as its factors, if it was some 2 to the power n, it was okay. But when it has anything other than 2 in its prime factorization, then you can say that this is the thing which is causing the problem. Now here the differences were 6 and 5. Here if you see, the difference was 6 and 5. Now 6 is 3 into 2, 5 is 5 into nothing. Okay, so this 2 can be ignored, and you can say the differences are 3 and 5. And now this 3 plus 5 is forming 8. So this difference was okay. So basically, whenever you have some factor of 2, just reduce that factor, remove that factor. So just see all the differences. If you have some 6 and 5 and there is some 12, there is some maybe 24 also. Just remove all the factors of 2 from this. 6 would get reduced to 3, 5 would be 5. 12 is 3 into 2 to the power 2. So remove this. This is 3 into 2 to the power 3. Remove this. It would remain 3, 5, 3, 3. So these are the things which are causing the problem. The factors of 2 were not causing you a problem. These are the things which are causing you the problem. So now what you can do, you can combine these differences 3 plus 5. If it is making something as a power of 2, then it's good to go. So again, this intuition is same from the problem C, I think, that we discussed today where you had to take a GCD because you can do some plus minus in there. So again, you can do some plus minus in the differences and obtain a value which you need to, which need to be some power of 2. And if there is some power of 2 and that is reduced, it would be reduced to 1. If it is 8, that is 2 to the power 3, and you remove this powers of 2 because we are removing this, it would become 1. So basically here again, what you need to do is just take the GCD of all these differences. After removing the powers of 2, just take the GCD. The value that you get in the GCD, if the GCD is 1, it means you can have all consecutive values. If the GCD is not 1, it means you cannot have. Here you see, if you look at this 258 or whatever that was, 2 8 13, here the difference was 6 and 5. Now you had differences as 6 and 5. First remove all the 2's from it. It became 3 and 5. Take the GCD of 3 and 5. It is 1. Since the GCD is 1, you would say, yes, you can. This is a brilliant set. So the way of computing the brilliant set is, for a given array, just take the differences between two consecutive elements, form the array of differences. Then for every difference, just divide it by 2 until it has some factor of 2 in it. So just remove factors of 2 from them. And then whatever array you get, just take the GCD of all the elements of that array. If that GCD is 1, it is brilliant. Else it is, if this is not equal to 1, this is not brilliant. That you can see. Now, once you know the way of computing it, what you need to do is you need to count number of subarrays which are brilliant. Basically, for a given array, you need to count. So uh, if you start from this, like here, if you take this test case, what all subarrays start with 1? So to count the subarrays, basically just consider all subarrays starting with 1. So it is 1 1, that's 1. So check that if that is brilliant. A single element is always brilliant, no problem in that. 1 3, is it brilliant? The difference is 2. It is brilliant. 2 divided by, remove them, 1. GCD is 1. Now once this is 2 and it is having a GCD of 1, now when you add elements to it, once the GCD has reached 1, whenever you add more differences, GCD of 1 with anything is always 1. So its GCD will remain 1. So once you have said that this 1 3 is brilliant, it means this, all of them would be brilliant. All of them would have a GCD of 1. So if you look at it, if you start with, if you fix a L, then up to some R, you would get something which is not brilliant. And after a particular point, everything would be brilliant. So basically, you can get an intuition of a binary search here, that up to some point, there would be brilliant. It would be not brilliant up to some point. After that, it would be brilliant. So instead of computing the number of brilliant, you can just compute the number of not brilliant and subtract it with n into n plus 1 by 2. N into n plus 1 subarrays exist minus the count of not brilliant. If you do, you would get your final answer of number brilliant. How to count the number of not brilliant? You start with L. Just find up to what extent you are getting not brilliant. Add the size of that to the answer. If you start with this, up to what extent you are not getting brilliant. If you start with this, up to what extent you are not getting brilliant. So you need to compute that. Now, again, you need to calculate this count in optimized way. This n is up to 1e5. So for every L, if you are just checking for every R 1 by 1, it would go off n square. Now, but if you want to apply some binary search that up to this range, what is this? You need to know the GCD of this range in some optimized way. So what you can do, you can use either a sparse table or a segment tree for that. You can use the range query thing. Either a sparse table would work. You can also use a segment tree if you wish. So what I'm doing is this differences. I'm just take the differences and reduce all those, remove the factors of 2, the final array that you get. For that final array, you just need to compute the basically number of values where the number of ranges where the GCD is not 1. That's what you need to compute. Like for this, first take the difference, like 3, 1, 3, 6, 10, 15, 21. If this was 1, 3, 6, 10, 15, 21. So if you need to calculate your answer for this, first what I did, take the differences. So difference, this is 2, this is 3, this difference is 4, this difference is 5, this difference is 6. You took the differences, remove all the factors of 2 from them. So 2 reduced to 1, 3 would be 1, 4 reduced to 1, 5 would be 1, 6 reduced to 3. Now, for this array, just count number of sub arrays where GCD is not 1. Here GCD is 1. Here GCD is 1, 1, 1, 1. So no problem. You need to count the number of subarrays where GCD is 1. That would be the values which are not brilliant, which you need to subtract from n into n plus 1 by 2. So this 3, its GCD is 3, not 1. This 5, its GCD is 3, not 1. 5, not 1. This 3, GCD is 3, not 1. So basically here, and if you take this range, it is 1, 1. If this GCD is also 1. So here only there were 3 values. This, and this. Only 3 ranges were there, which were not 1. So my final answer was n into n plus 1 by 2. N was 6 here. Okay, 1, 2, 3, 4, 5, 6. So 6 into 7 by 2 was 21. So there are 21 subarrays. Out of them, 3 were not brilliant. So 18 was my final answer for this test case, like you can see. 18 was my final answer for this second test case. So I just need to compute this 3 through a sparse table or a segment tree you can use. So you would compute the number of subarrays which are whose GCD is not 1. So it's a like simple range query question. It has become after this reduction. For this array, just find the number of subarrays whose GCD is not 1. So if you start, since you are taking GCD, if you take start taking GCDs, once it would always reduce. GCDs would always reduce. It's a reducing function. So if you start with 1, here only it's 1 already. So you would add plus 0 to an answer. If you start with 3, here you would compute up till which point you would have a non greater than 1 GCD. So 3 L's are the where you have greater than 1. 3 to 1, once you move this R to here, it would become great equal to 1. So after this, all the values would be equal to 1. So for every L, when you fix a L, apply a binary search to find that's one way, like to D of a range, pre-compute your sparse table. So you can pre-compute your sparse table or a segment tree. So through that, you would get the GCD of a range in O of log n. In O of log n, you can get the GCD of a range. Now, once you fix an L, if you apply a binary search and find if this GCD of this range is greater than 1 or not, that inside the your check function would be just checking on that. So binary search would take log n time, and you're checking the query of your sparse table or a segment tree would take log n time. So in log n into log n, and for every L from 0 to n, it would be n if you fix a n. So it would be n into log n square would be your final term complexity. If you are doing binary search with a sparse table, there would be one more log n for calculating the GCD. So it may go up to log n cube. You can try this solution. It may give a TLE or it may get accepted, but I just optimize it a little bit more by removing one log n factor by using the sparse table thing. That by instead of doing the binary search, I'm doing the query in the sparse table only to find for a fixed L what is the minimum R, so that my GCD for the range, my query for the range L to R is greater than 1. Minimum R, so that So this thing can be computed in log n time. So this 2 log n squared that I was using inside a binary search, I can compute this in a single log n by using a query of my this kind of query from my sparse table. You can also do the same thing in your segment tree. You can update the query thing like that. How I'm doing this, I'll show you in my code. Okay. So I hope the logic is clear. I can move to the code now. So what I'm doing here is I took the input. After that, first thing, I converted my actual uh, vector into an array having the differences with reduced by two factors of two. So for every, I'm going to all the differences. X is the difference between AI and AI minus one. So difference between any two consecutive values, I'm going to all the every such differences. And if this is greater than 0 and its mod is equal to 2, if there is some factor of 2 in it, divided by 2. So this way I removed all the factors of 2 from it and I pushed that value into my vector. So this is my new vector in which I'll apply my queries of my sparse table. So I build my vector. So here I've written the functions of sparse table here. So this is the build function of my sparse table, the pre-computation thing. I build my sparse table. Now, my initial answer would be n into n plus 1 by 2. Now, whatever non-brilliant arrays would be there, that would be subtracted from this. Okay. Now, I went to every I fixed my L. So my L is now fixed. So I is my L basically. You can, instead of I, you can replace it with L. So I'll fix my L. Now this difference vector is of size n minus 1. That's why I'm only going till n minus 1. Now, if that is 0, one small edge case you have to consider here is that if the difference is, let's say there is 90, 90, 90, the differences is 0, then in, instead of this 0, like you would see GCD for in the difference vector, if you get, let's say this test case only, or let's take this. Okay, this one edge case you have to consider is if you have this array, you converted it into a difference array. This difference is 0, this difference is 3, this is 1, this is 4, and this is 3. Once you have converted it into a difference array, now if you take this as your L, GCD of 0 with anything is that thing. So GCD with 0 would be 0. And then GCD of 0 and 3 would be 3. So basically by moving to the right, my GCD should always reduce, but it is 0 initially, then increasing and then reducing. So in 0, it is to showing a little different behavior. So zeros I would consider separately. It is a 0. It means what? Both are equal. It means I can either take this one or this one as my range. It would, in the set, when both these one are put, it would be a single one. It would not matter. So for zeros, I would just say that with this as the fixed L, whatever values for whatever which is not brilliant, if I include this 0 as the difference, like for this, whatever which were not brilliant, if I include this one also, it would still remain not brilliant. So if I get some zeros, what I'm doing, I'm taking a variable f. In that, if I have 2, 3 zeros, uh, if it is 0, I'll just do f plus plus and continue. Whenever I get a non-zero, instead of adding the size of my range to my answer, I'm adding f into that size. If there is no 0, f would always be 1. So I would only add this size. What is this size? I'm doing a query to find what this query 2 is doing is, for a fixed L, the maximum R, or it is actually minimum here. In this case, I've written maximum, but it's minimum. So, or the maximum only. So yeah, it's maximum only. The maximum R such that L2R is greater than equal to val. In val, I'm passing 2. So it means the maximum R, uh, the maximum to the right we can go so that the GCD is greater than 1. Once it becomes 1, it is brilliant. We need to compute the non-brilliant. It would be till where it is greater than 1, which is greater than equal to 2. I'm in val, I'm passing 2 here. I2. So this R I would get. So in my sparse table, like this, I'm doing the query and computing that maximum R so that the query is giving me greater than one value. My range GCD is greater than one. So what I would add to my answer is R minus I plus one. So from L to R is the range, R minus I plus one is the size of the range that would get added, that would get subtracted from my answer. And it is into one, it is only one time if there are no zeros. If there is some zeros, like if there is a 0 and a 3, then whatever the answer for this 3 would be, same would be for this also. So here I'm not computing, I'm computing here and then multiplying it by 2. So if I had 2 times 0 and then 3, then for all these else, I would have that answer. So I'll multiply by 3. So that's why I'm doing F plus plus here and multiplying by F. And I'm storing F equal to 1 once I get a non-zero value. Again, I'm resetting my F to 1. So this way I'm handling that edge case also, and I'm computing my, so this is the code for the problem F. I hope it is clear now. So thank you for tuning in. We can end there.